Thank you all for joining us this morning. And our first speaker of the morning session is Emil Wiedemann from University in Germany. And we're very happy to have him speak. And he's going to speak on statistical solution for the 2D Euler equations. Thank you, Emil.
Yeah, so thanks again for the kind introduction and for the invitation to this conference, which has been very interesting and nice so far. And I would like to talk about a recent project together with my PhD student Raphael Wagner at University, where we looked into various concepts of statistical solutions for the Euler equations. And considered the existence theory in classes for which we know the existence of deterministic solutions. Like that's the most you can hope for. So if you don't have deterministic existence, you wouldn't expect existence of statistical solutions. But we'll get there. So first, okay, we've seen this many times also during this conference. There are the incompressible Euler equations here in velocity formulation that everyone certainly has seen. And you also know, and we have heard this in a couple of talks this week, that there is another maybe more suitable formulation that is very specific to the two-dimensional situation. So we can define the vorticity, which is the curl of the velocity, which in 2D is just a scalar quantity. And so when we take the curl of the velocity formulation, then after a short computation, you arrive at this transport equation. You can see when I mark something in the slides, right? So this is the transport equation for the vorticity omega, which is transported by its own velocity field. Now, this in itself wouldn't be, well, it would already be of some help, but it wouldn't be a closed equation unless we could formulate this in terms of the vorticity alone. And for this, there is a connection between vorticity and velocity. So the vorticity is the curl of the velocity, and you can somehow invert the curl to obtain the velocity from a given vorticity. And so this is something that we know as the Biot-Savart law, where I have here, well, this singular integral operator that I apply to the vorticity in R2. And this operator has the nice property of being Calderon-Zygmund in the sense that you have estimates like you can estimate the gradient of the velocity in LP if you can estimate the vorticity in LP, which you can because we have this divergence-free transport structure, which means that at least formally, we have the conservation of LP norms. Yeah? In fact, I can take any renormalizing function and that would, the integral of which would be conserved under the evolution because we have this incompressible transport. So I will not bother very much about the renormalization property. The only thing we need to know is that in all situations to be discussed here, we can at least obtain some renormalized solution for which we then have this equality or this conservation of LP norms of the vorticity. So there is one technical issue that I didn't completely want to ignore in this talk when we work on the whole space R2, because in the end we want to consider, say, vorticity in LP, for instance. And now a simple observation is, well, if the velocity has finite energy, which means that it's in L2 on the whole space R2, then clearly the integral of the vorticity, which is the integral of the curl of the velocity, that would just be zero by integration by parts. So if we considered only velocities of finite energy, we would have to work in a very restricted class of vorticities whose integral is zero. So we prefer to work in a slightly more general framework, which is known as, well, the class of velocities with a radial energy decomposition. So what does this mean? It means we have a velocity that we can split into two parts. The kinetic part, that is, that is really a velocity field of finite kinetic energy, whose vorticity will then correspondingly integrate to zero. And we have this kind of correction, which is a stationary solution of the 2D Euler equation. So the kinetic part is in L2, but the stationary part is, well, it has this form. And the important thing is that it is a scalar multiple of the perpendicular vector of x. So it is a stationary solution that, whose flow lines are circles. So the vector field will just rotate the fluid, and it's easy to see, and it's well known that this constitutes a time-independent solution of the 2D Euler equations. Now, if you look at the order, so r is the radial variable, so the mod of this solution here will be like 1 over r, which slightly fails to be in L2. Yeah, so this is where this kind of infinite energy comes from. And the integral here, I mean, don't worry about it too much, but that is written in a way such that the corresponding vorticity of this sigma would exactly be g of the radial variable. Yeah, and g is just you can give some CC infinity function. So that will give rise to a part of the vorticity that is radially symmetric and that is smooth and compactly supported. In any case, so this allows us to consider vorticities whose integral is not zero, but is any real number. And the spaces of velocities that have radial energy decomposition with this given integral of vorticity, that is an affine space, which is denoted EM. And then if we take the union over all EMs, we will simply arrive at the space of E, which is the space of velocities, which admits such a radial energy decomposition. And the important thing to note is that any class of vorticities that we will consider in this talk will give rise to a velocity that has such a radial energy decomposition. Now, let me recall some well-known existence results that were also mentioned in other talks of Maria Colombo and Gennaro Ciampa during this week. The most classical one is the theorem of Wiedemann, which tells us, okay, if I start with a velocity, okay, that has a radial energy decomposition, but most importantly, where the corresponding vorticity is L infinity bounded. That is the important thing about the Wiedemann class. Then we have unique solutions that also remain in this class. So for all times, the vorticity will remain bounded. Now we can now lower our assumptions on the vorticity. There is a result by Di Perna and Maida. Actually, often this paper is cited for the theorem that I also mentioned here, but their paper was more about more interesting stuff related to harmonic analysis in the case p = 1. But one thing that they prove, and where we have seen an outline of the proof, I think in Gennaro's talk, is the following. So now if my vorticity is no longer bounded, but it's only an LP, where P is strictly greater than 1, I have a similar existence result. So then I will also have a weak solution with the given initial data, where the vorticity also remains in LP for all time. In fact, the LP norm will be conserved if the approximation in the proof of this theorem is chosen somewhat reasonably. But we no longer have a uniqueness statement here. In fact, as we have also heard, there is reason to doubt that we have uniqueness. So what we know by this by these preprints of Wischig and this nice presentation by the group around Camillo and Maria, is that in fact we do not have uniqueness, at least when we allow for external forces. And there's also the very interesting convex integration result by Elia and Maria, that was also discussed by Maria, about the non-uniqueness of solutions when, okay, we don't have LP, but we have something like a weak L1, so slightly larger than L1. But for L1 itself, there is the result of Vecchi and C.J. Wu, who essentially say there is a small caveat that somehow we need the compact support of the vorticity, but essentially they extend the existence to the p=1 case. Now, a very interesting thing is the theory of Delors, where instead of L1, we consider bounded measures. They have to have a distinguished sign, so without loss of generality, we're talking here about non-negative measures. Well, what is also usually taken as an assumption is that the measure is in h-1. This is in fact implied by the radial energy decomposition of the velocity field. But in any case, you would have also the existence of weak solutions of the Euler equations. You actually have to use the velocity formulation because the vorticity formulation breaks down as soon as the vorticity is not at least in L4/3. But in any case, you have weak solutions to the Euler equations, which also stays in this class of non-negative measures, which are in h-1. So about this h-1, this looks like a technical thing, but it actually tells what kind of measures you can handle with this theory. So for instance, a Dirac measure would be excluded. There is a very interesting theory, which is actually more like an ODE theory than a PDE theory, of so-called point vortices, where you take the data for the Euler equations to be a vorticity that is a Dirac measure or the sum of certain Dirac measures. And that gives rise to very interesting dynamics, but this is not covered by Delors' theorem because a Dirac measure would fail to be in h-1. So essentially what the Delors theory is about, well, it's about so-called vortex sheets. These would be vorticities that are concentrated on, say, smooth or at least rectifiable curves. So you would have the situation where the velocity would have a jump discontinuity across the surface. This is in fact a very important problem in applications when you think about the Kelvin-Helmholtz instability and things like this. Anyway, so this was just a brief review of classical theory. It turns out, though, that I mean, this is, of course, at least since Kolmogorov and probably much earlier, there has been this this observation somehow that turbulent flows behave in a very unpredictable way, so that a deterministic description would not give you a lot of information. Like take this vortex sheet, for instance. Well, if the vortex sheet is flat, then you get a stationary solution of the Euler equations, which is just given by this shear of the velocity, and that's it. But this is highly unstable. Yeah? So as soon as you have just the slightest perturbation here, you will see a Kelvin-Helmholtz instability, and your solution will behave completely differently as this kind of cheap stationary solution that you can explicitly write down. But it also turns out, and there is impressive numerical and experimental evidence for this, that in such unstable turbulent situations, although each deterministic solution behaves in an unpredictable way, certain statistical parameters like the mean flow or the variance of the flow or the so-called structure functions, which are also part of the two-point statistics of the flow, they would behave quite regularly. And this is somehow the motivation to consider probabilistic concepts of solution. And today I want to talk about 4 different frameworks. Now here for the beginning, I just listed 3 of them, but the first 2 are frameworks that go back in the context of Navier-Stokes equations to Feuer-Sprody and to Vichy-Korsakoff. And these are solutions that people would refer to as statistical solutions. And the third probabilistic concept is due to Di Perna for conservation laws, and then Di Perna and Maida for the Euler equations, which would not be called statistical solution for reasons that I will explain. But in any case, they also fit into the framework of probabilistic descriptions. Now, let me try to explain just very roughly the general idea of these 3 approaches. So I put here first Vichy-Korsakoff, not because of historical chronology, because Prodi and Feuer were first, but just systematically, I think one extreme end of all these theories would be this Vichy-Korsakoff approach, where you take the set of solutions of a certain PDE, say the Navier-Stokes equations or the Euler equations. So you take some class, say Leray-Hopf, of solutions, and you just put a probability measure on them. Yeah? And then this is just one probability measure, which depends on nothing else. So then what about the dynamics of the equations? Well, the dynamics obviously cannot be on the probability measure because it has no time dependence or anything. But the dynamic is simply encoded in the support of that measure. Yes? So you just have to make sure that your measure lives on a space of solutions that thereby respect the dynamics of your PDE. Now, Feuer-Sprody take a different approach. They consider a parametrized probability measure that is parameterized by time. So that probability measure can actually be subject to a dynamics. The probability measure for each time, or for almost every times, lives on a suitable function space. So that could be the energy space for Navier-Stokes. That would be then L infinity into L2 and L2 into H1. Or for Euler, it would be one of these spaces where the vorticity is in a certain class, say LP. And then the dynamics of this measure of this statistical solution rho t is governed by what is sometimes referred to as a Liouville type equation, and we will see such a Liouville type equation later in this presentation. And kind of the other extreme would be Di-Perna-Maida. So you could parameterize the probability measure not just by time, but also by space. And then the probability measure would only live on the space of velocities, yeah, like kinematically, the space of velocities, which is just R2. So this is a measure not on a function space, but it is a measure on R2 or R3. And the dynamics will then also be encoded in, well, a certain PDE, which, however, is not really a PDE, it's just a linear constraint for the first two moments of this measure rho. So for interpretation, if we compare these latter two concepts, the Fourier-Prodi and the Di-Perna-Maida, the Fourier-Prodi tells you, okay, for every time, what is the distribution of velocities in a function space? So it's a probability measure on function space. And this allows you for every time to describe the full statistics of the velocity in space. Now, this is different for Di-Perna-Maida. Di-Perna-Maida only tells you, okay, what's the probability that at a given point x, at a given time t, the velocity is this or that vector. In particular, these measure-valid solutions by Di-Perna-Maida cannot describe the higher order statistics. They cannot describe correlations between the velocity at the same time, but at different points in space. And this means that the Di-Perna-Maida framework kind of contains much less information than the other frameworks. We will see later on an approach to kind of fix this issue and to work with Di-Perna-Maida type measures that also kind of includes the higher order statistics of the flow. So another remark is that this all these statistical solutions make sense or are useful only when we do not have an evolution semigroup. Because if we have an evolution semigroup, because the equation is well posed, we have unique solutions, so we have a solution operator, then in fact the unique statistical solution, at least in this Vichy-Korsakoff sense, will be the push forward of the initial distribution by that solution operator. So there is not much insight to be gained here. So in the Udovich class, for instance, yeah, that is what you do. You have the push forward of the initial distribution under the solution operator, and in a sense, that's the end of the story. Yeah. And for the Fourier-Prodi, also, if you have a solution operator, you can get in this way. No, that's the other one. This would be the Fourier-Prodi statistical solution. There might be other ones, but at least you have one, and this seems to be the natural statistical solution. In fact, that was part of the motivation, I guess, why people decades ago developed this notion of statistical solutions, because the 3D Navier-Stokes equations in the Luray-Hopf class, uniqueness is not known. I mean, now we actually know non-uniqueness, as we heard from Maria, but in any case, we don't have a natural solution operator. Well, another important observation that was made in the context of Navier-Stokes equations is, so the observation was made in a quite recent paper of Fourier, Rosa and Timam, is that there is a connection between the first two notions that I mentioned of statistical solution. So a Vichy-Korsakoff measure, that would live on a space like continuous from time into some function space, maybe with a weak topology. But you can just project that down to time. Yeah, so you can take the projection, you can kind of slice the Vichy-Korsakoff measure And that will give rise to a Fourier-Prodi measure. So that's the connection between these two concepts, and that holds in much greater generality. So talking about a greater generality, most of the work on statistical solutions that I'm aware of is in the context of 3D Navier-Stokes. But of course, the abstract functional analytic / measure theoretic framework is not specific to Navier-Stokes, and the most general framework that we found, actually, Raphael became aware of this paper by Bront, Simondini, and Rosa. That is a very general framework for statistical solutions of like a general class of evolution equations, or not even evolution equations. So let's look at that. You can see how general it is because kind of the state space is just a Hausdorff topological space. Very well. We have a time interval, and we have some set U, which is a subset of the space of locally continuous functions from time into that Hausdorff state space. Yeah. And we want to define a trajectory statistical solution. So that would in spirit correspond to the Vichy-Fulsikov notion. So that is called a U trajectory statistical solution. So rho lives here. Yeah, rho lives on the space of functions from time into that space. If, okay, technical thing, rho should be irregular, so it can be exhausted by compact sets. But more importantly, rho is carried by the prescribed set U. Now the definition is even more general, so it's supported by a Borel measurable subset of U, because U would not necessarily have to be Borel measurable. Let's not worry too much about these things. In any case, the support of rho is in this given set U. And that's what in the most abstract setting can be called a statistical solution or a trajectory solution. Yeah. Now, first thing when I saw this that came to my mind is, wait a minute, yeah. So it's called a solution, but a solution of what? Yeah. So in fact, the problem that you want to solve is completely encoded in the set U. Yeah. And typically you would think of U as some set of solutions of some problem. So in our case, it will be the 2D Euler equations in a suitable function class. And then, so they also have a notion that is closer to the Fourier-Prodi, that would be the trajectory solutions. I will get back to that later. But what Bronzi and collaborators have is a general existence result in this framework. So the assumptions here are the same. We start at some initial time t0, and we have three conditions now on our sets U and X. First condition tells that the projection of this set of solutions, say of the set of deterministic solutions, the projection to the initial time should be all of the phase space, which simply means that for every element of X, I can find some deterministic solution to my problem. And this already tells us that we can only expect statistical solutions in a class where we can solve the existence problem deterministically. Now, secondly, well, that is a bit of a technical thing. I need a family of compact subsets of phase space with a property that any possible initial data, so every irregular Borel probability measure, is not just irregular with respect to all compact subsets, but it's irregular with respect to this specific family of subsets. Now, don't worry too much about this. It just means that this family of compact sets, which we call K-primed here, should be just large enough to kind of determine every Borel measure on that space. And the third condition is that this family of compact sets should not be too large, because we need this kind of compactness that we usually or classically use to prove existence of a certain nonlinear PDEs. Yeah? So this is the third condition. For every compact set in this specific class, this set here, so it's the set of solutions that start initially in this set kappa. And that set should be compact with respect to the appropriate topology that is encoded in the topology of this Hausdorff space X. Yeah. And if we have these three ingredients, then we have existence of a trajectory statistical solution with the corresponding initial distribution mu0. Now, this is very general. Let's get back to the Euler equations, and let me just briefly mention the work on the Euler equations. So I already said that most of the work in this context is on the Navier-Stokes equations, and indeed there is not much literature on statistical solutions to the Euler equations. There are two works by Dongbo-Che in 1991, where he shows existence via the vanishing viscosity limit. There's a work of Peter Constantine and Jiahong Wu. So that's a different Wu from CJ Wu with the L1 vorticity. But in any case, they also study the vanishing viscosity limit and thereby get existence. They consider both types of statistical solutions. There is a more recent work of Jim Kellier, who looked at the Udovich class. And all these three works, well, they get existence for 2D Euler in case of vorticity that is, well, at least L2. You know? And a very different kind of direction that is in my paper with Ulrich Fjordholm. So we considered statistical solutions in a seemingly very different setting, which was introduced by Fjordholm, Lanthaler, and Mishra a few years ago. And I will say more about this concept of solutions at the end of the talk. But we also considered like a different question, not the existence, but we considered Onsager's conjecture, and that was 3D and so on. So that is not really related to the topic of today's talk. Now, we have this general existence result in this framework of Bronte and collaborators, and we want to use that for 2D Euler. So let me just, for the purposes of this talk, focus on the case where p is between 1 and infinity, because the Udovich business is a bit boring. As I said, you have a solution operator that just gives rise to your statistical solution. But here we don't have a solution operator, so things start getting interesting without being overly technically complicated, as it would be for p equals 1 or for the Delors class. So let me consider this case here. Our phase space is now the set of velocities with radial energy decomposition, whose vorticity is in the appropriate class. Okay, and the space U, where we want our measure to be supported, is the space of weak solutions that is also of sufficient regularity. So the solutions should be continuous into that phase space. And well, by Calderon-Zygmunt, we get a W1P log estimate from the vorticity. And plus what I didn't spell out here, usual a priori estimates that would mean that the vorticity is preserved, or at least bounded by the initial vorticity, and that we have a certain type of energy inequality, or energy estimate for the velocity, which is not as straightforward as you may be used to, because, well, we work in this class of infinite energy velocities, which have a radial energy decomposition. It turns out there is some a priori estimate, at least on the finite kinetic part of the velocity. Anyways, that constitutes our solution space. And then the theorem is that, okay, if mu naught is any Borel probability measure on phase space, then this serves as an initial data. Then there exists a U trajectory statistical solution in the sense defined previously, whose initial data is the given one, and also we have a uniform bound on the vorticities, of course. Yeah. Now, we do want to use this general framework of Bronzi and Mondaini and Rosa, but let me give you a more or less self-contained proof sketch that does not use this general result, so just so you understand better what is going on here and what is the idea behind the existence of statistical solutions. So for preliminary observations, we basically check the assumptions of this general existence theorem. So one thing is that our state space is chosen in a way that it is Borel measurable in this normed space of radial energy velocities, which turns out to be a Polish space, which has the nice consequence that any Borel measure is automatically irregular. So we don't need that assumption. That's a nice thing. And then we have to choose this family of compact sets in a suitable way, and we do it by choosing sets of this form. So we take something that is compact in phase space, but also whose vorticity is compact in this kind of vorticity space L1 intersect L infinity. And that turns out to give us a good class of compact sets which has the desired properties. So one of the desired properties was that, okay, our any Borel measure will also be irregular with respect to this specific class of compact sets. And the other condition was that, yes, every element of the set, every set of this form will be compact in the space of trajectories. So this is something that, I mean, I don't want to say this is terribly difficult to check this, but it's something that's non-trivial. So it's some work you have to do whenever you want to take this super abstract framework and apply it to an actual problem. So so then how do we prove existence then, and how do Bronzi and Mondaini and Rosa prove existence? So that's an idea that was introduced by Feuerge and collaborators a few years ago. It's not the classical existence proof of Feuerge for Navier-Stokes for statistical solutions, but it's actually a very nice idea. So first of all, okay, if my initial measure is already supported on one of these compact sets, call it kappa naught, we take the set of non-negative Borel measures that are supported on this compact set of mass less or equal 1, then that is a weakly compact and convex set. So we can apply the theorem of Krein-Milman, which means that any element of a compact convex set is the closure of the convex hull of its convex extremal points. Yeah, that's a nice theorem of Krein-Milman. And the convex extremal points of the set of these measures are precisely the Dirac measures. So in other words, we can approximate our initial measure mu naught by a finite convex combination of Diracs centered at velocities that are all in this compact set. And now we can use the deterministic theorem. So we choose, I guess we need the axiom of choice here, but we choose for each initial velocity, which is deterministic, some weak solution that is still in our designated space of solutions. And that gives rise to a discrete probability measure, which just has this form. So in a sense, we push forward the initial velocities to certain solution trajectories, and that will be our new measure. And now, because we checked that now these measures will be supported on kappa, which is compact, which is one of the things we had to check initially. Since a compact metric space is in particular separable, then we can use the sequential Banach-Haller-Oglu theorem to get a limit measure rho. And then, okay, you can check that the limit measure rho does what you want. So it takes mu naught as its initial data. It is supported on kappa, which itself gives rise to it means that the statistical solution which rho represents is then in fact supported on this set U of trajectories. And finally, at the beginning of the proof, we had this assumption that the initial measure is supported on one of these compact sets. But now, thanks to the fact that these sets are large enough so that we can approximate or we can characterize mu naught in terms of this family K primed, then we can conclude the proof in its full generality. Yes, now this was the trajectory statistical solutions in the spirit of Vichy-Korsakoff. Now you can do similar things with the Fourier-Prodi solutions. You call that, if you leave the realm of Navier-Stokes equations, that can be called a phase-based statistical solutions of a general evolution problem that has this very general form. And a family of measures that satisfies, well, certain technical conditions, but most importantly, the Fourier-Liouville equations, they look like this. Yeah, that will be a phase-based statistical solution. So these equations here govern the evolution of that measure in time. That's something that you might have seen. It looks a bit like the weak formulation of the corresponding evolution equation. And as I noted before, it has been proved that if you have a trajectory statistical solution and you project it onto time slices, then in fact that will be a solution also in this different sense. So in the end, what Raphael and I show is that, so there will be a preprint out quite soon, is that in all the mentioned classes of initial vorticity, we can have the existence both of a trajectory and of a phase space statistical solution. In fact, okay, for Udovich, the trajectory solutions are in fact unique, but that's maybe not a big surprise. Yeah, so anyway, it's nice to see that some of the preliminary works, which had quite specific assumptions on the initial vorticity, that they can be generalized so that we really can say that whenever we have a deterministic existence theory, then we also have a statistical existence theory, both in the trajectory and in the phase space sense. Now, finally, for the end of this talk, let me just briefly mention the connections to other probabilistic concepts. I mentioned the measure-valued solutions of Diperna and Maida, where, well, okay, you just take parametrized measures, you take probability measures on the space of possible velocities at each point x and t in space-time. And you have something that looks like the Euler equations, but note the only thing you are restricting here are the first two moments of that probability measure. So the expectation and the covariance, somehow, because you only consider the one-point statistics, it is easy to obtain the existence of measure-valued solutions, like even if you don't have a deterministic solution theory. So even in 3D, for 3D Euler, there is no deterministic existence theory, but these measure-valued solutions are so kind of weak that you can easily show existence. And it comes at the cost that you can only describe the one-point statistics of the flow. Now, there is this idea of FLIRT, Landthaler, and Mishra that you could somehow...
So, Emil, a couple of more minutes.
Okay, thank you. Yes, I'll try to speed up. That you could somehow use this idea of Young measures, like of parametrized probability measures, to gain information about the higher order statistics after all. So since I have no time left, let me just tell you that, okay, there is this framework where you have an infinite hierarchy. This should be rho everywhere. You have an infinite hierarchy where rho 1 is the measure-valued solution of Diperna-Maida, and rho 2 is a kind of more complex Young measure that lives on kind of, a copy of state space with itself that encodes the 2-point statistics and of the 3-point and so on. Yeah, that sounds like a complicated thing. In any case, what we did here also with FLIRT is to tailor that notion to the 3D Euler equations. Now that seems like a completely different approach than the Fourier-Prodi approach, where you just have a probability measure on function space. Instead, we have an infinite hierarchy of probability measures on like copies of Rn with itself. It turns out, however, so the first theorem here in the paper by FLIRT, Landthaler, Mishra, it turns out that there is some kind of equivalence between these correlation Young measures, these infinite hierarchies on the one hand, and a single probability measure on the function space. And this was used by Raphael already in his master's thesis to prove that, yes, due to this identification, we can in fact have a one-to-one correspondence, perfect identification between a statistical solution in the FLIRT, Landthaler, Mishra sense and a statistical solution in the Fourier-Prodi sense. So in the end, we have nice links between all these solution concepts. So let me just summarize the last point here. We have trajectory solutions. If I take time slices, if I project them down to a certain time, then I get phase-based solutions. So that's the relation between these two. Then the phase-based solutions are equivalent to FLIRT, Landthaler, Mishra solutions, at least for Euler. Would be interesting to put that into the general context. And finally, the measure-valued solutions contain much less information, but they can be represented as the first part of the FLM hierarchy. So yeah, we see that we have really nice connections between all these various concepts. So thanks very much for your attention.
Thank you, Emil, for the very interesting talk. Is there any question?
I do have one, if possible.
Yeah.
Hi. First of all, thanks for the nice talk. I really enjoyed it. I wanted to ask maybe two questions. Like, first of all, how your solution are related to the generalized solution introduced by Brenier?
Mm-hmm.
Because like also that there must be some connection. I think there is actually some connection with the Young measures, and if you do also have a sort of uniqueness of an associated pressure to your solutions. And am I right if I think when you're approximating your measure with that delta, that basically this delta is like the evaluation over volume preserving diffeomorphisms in the case of Euler?
Yeah. Well, as you say, the Bernier framework is a Lagrangian one. It's a variational one. And what I talked about here is an Eulerian setup. Yeah, it's a good question. I believe when I was a PhD student, my advisor asked me a similar question, and we didn't get very far. So I can't really tell you a lot about. So I'm pretty sure that nowhere in the literature you can really find a theorem that tells Bernier solutions are equivalent to measure valued solutions or something like this. Yeah, I really can't say much about that. Somehow the spirit, yeah, you take this kind of multi-valued or you measure valued trajectories, and so that seems very similar. Yeah, but I can't say really more about it.
Okay, thank you.
So Lucio, you have your hands up.
Yes. Hi. Thank you very much for the talk. I wanted to ask if you explored maybe possible connections to sort of another closely related line of research, which is the one about basically measurable selections for solution semiflows. Because I mean, there have been several works. Okay, for 2D Euler, I don't know of any, but definitely there are for real solutions of 3D Navier-Stokes or for 2D compressible Euler. And it seems like exactly the point you mentioned at the beginning, like, okay, if I have my solution map, the statistical solution will just be the push forward of the initial measure, can be generalized to these measurable semiflows, which can be constructed in many situations in which you don't know if you have a uniqueness actually.
Yes.
And I mean, this also partially seemed to transpire from the proof. I mean, when you said we need to choose and we use the axiom of choice, and then in principle, what you're doing is measurable selections.
Yes, precisely. That is, yeah, that's something so the point is this is still work in progress, and of course I talked about this with Raphael because I think you're referring also to these beautiful papers of Breit, Feiressel and Hoffmannova that are very recent, so that they have a theory where I'm sure that would also apply to 2D Euler in these various functional settings. So their theory is kind of very unspecific for the particular system under consideration. And I'm sure that would work for 2D Euler, and I'm sure that would be an alternative and very interesting way to prove existence of statistical solutions, to take such semiflows, which are not unique, but you can just choose some semiflow that will give you a statistical solution. And that would certainly be an alternative approach that we wanted to explore. Yeah, but thanks for pointing it out.
Just add one last remark. I mean, exactly, I was referring to the works by Hoffmannova and collaborators, but just to give credit to people, I think that line of research was initiated by Fandoli and Romito, at least for 3D Navier-Stokes. I mean, even before, but I mean, there are already papers from, I don't know, 15 years ago, I think, exploring this kind of things. Thanks.
Other questions or comments? I don't see any. So let's just thank again Emil for the wonderful talk. So our next and actually last speaker of this morning session is Camilla Nobili from Hamburg University in Germany, but soon to be at University of Surrey in the UK. It's a great pleasure to have Camilla speak here. And she's going to speak on the effect of boundary conditions for the velocity on scaling laws in the Rayleigh-Bénard convection problem.
Thank you very much for the invitation. I would have really loved to be there with you in Pisa. And I'm anyhow very honored to talk here. And I really enjoyed this workshop. And I hope that even if we cannot meet, we keep on doing this workshop because they are very fundamental for our research. So I want to talk about some observation that I've been doing, or some topics that I've been exploring recently, and namely, what are the rule of boundary condition in heat transport properties of turbulent fluids. So in particular, I will try to investigate this on a problem that I know pretty well, which is the Rayleigh-Benach convection problem. But this type of observation that I will do today, they can be applied to a number of other applied problems. So I will do a sort of a panorama on what's known, and then eventually I will talk about a recent work with Theodor Drivas and Huen Nguyen. And just before starting, I have to dedicate this seminar to Charlie. Okay, so let's go back to the physical picture. So what's happening in a finite box, which is full of a certain fluid. And so you are heating up at the bottom and cooling down the top. So this is something that, so this type of experiment, especially the Italians know it very well, because I mean, cooking pasta, this is exactly replicating this type of experiment. But nevertheless, this type of physical description is modeling many type of phenomena in physics, especially meteorology and oceanography. I will not go into detail, but there are a myriad of different applications to that. So in particular, so what happened when you have these differences in temperature? So the differences in temperature trigger differences in density, and then you will see that at some point convection rolls start to appear, and then eventually, if the heat is very strong at the bottom, then you would see the stabilization of these convection rolls and chaotic turbulent dynamics in the box. So in particular, so remember also I connect a little bit with what Michele Dolce was talking yesterday about, because he was looking at a Boussinesq system. So warm parcels are less dense and they are rising up, and the colder and denser parcel are moving down, and then you have this convection type of movement. So it's relevant to ask ourselves, so what are the heat transfer property inside this container? And again, this then can be translated to application, for example, to building up very efficient heaters, or to cooling down system for computers and nuclear power plants and so on. Oh, I'm not in full screen. Let me, sorry, 1 second. I didn't realize that. Okay. So the Rayleigh-Benach convection model, which is essentially now describing this phenomena that I was talking about before. So is this one. So you consider a box of finite height. Actually, all the system has already been non-dimensionalized. So the height of the box is 1. And then you have a lateral side length, let's call it L. And inside this box, we have to describe this type of convection phenomena. So we take a temperature, which is advecting and diffusing, and is advected by a velocity field U, which satisfies the Navier-Stokes equation with for divergence-free vector field. So we have an incompressible fluid inside, And you see that this system is instantaneously, well, is slaved. So there is a direct feedback. So we're not talking about passive scalar, but active scalar. And you have that the temperature is 1 at the bottom and 0 at the top, mimicking these differences in temperature. Now, I will just leave very generic that you have to assign some boundary conditions to the velocity. And let me, before starting then all the whole discussion about the boundary conditions, let me talk about these 2 parameters that appear here. So these parameters appear after you non-dimensionalize the system, and in particular, they really encode all the physics of the problem. So the Rayleigh number is a control parameter and depends on the constant of gravity, which points upward and downward, and then you have the coefficient, expansion coefficient alpha, and then you have here the temperature gap and the height to the power 3. The height, this is the physical height of the box, divided by nu and kappa, which are the kinematic viscosity and the thermal diffusion coefficient. By the way, so what I want to stress on the Rayleigh number is that it depends on the real temperature gap that you have in your experiment and this height to the power 3. So this is what you have to remember. So again, this is a control parameter, so it depends on the setup of your experiment, while the Prandtl number instead is a material parameter, depends on the fluid you work with, okay? So it's very different to work with air or mercury or other type of fluids. And obviously, even if at the experimental level, it's very complicated to change fluid. Now I will tell you why. So as I was just right now describing you, the different fluids have different Prandtl numbers. And you see that, so looking at water, which has Prandtl approximately 1, air, well, between 1 and 10. So air, the Prandtl is slightly less, but then oils, for example, the Prandtl number is rather large. And for liquid methods instead, the Prandtl number is very low. So you have a variety of fluids you can, with which you can do the experiment. And obviously, the experiment with these fluids for different reasons are relevant. And we will see later in the mathematics what it means to change a Prandtl number in terms of regularity and so on. The Rayleigh number, instead, we were again describing it as a control parameter. So now I report this beautiful, so I've seen personally this experiment. So this is an experiment in Ilmenau. So this barrel is about 7 meters tall. So they are really trying to measure the heat transport property with air inside this huge barrel. Why air? Because the problem of a 6 meter tall barrel is that putting fluid means that you have to have a security measure, and like fluid should not escape. So air is the fluid with which they can actually work. Anyhow, so this is very impressive. If you happen to be in Ilmenau at the TU, you should go and watch it. It's quite amazing what they are doing inside. So let's start with the mathematical, the goal. So it's easy to extract the heat flux from the temperature equation. In particular, the heat flux you detected when you use the divergence-free condition on U, and then you see that this ut minus grad t, so this is exactly what sometimes in physics you would write it as J, so the heat flux. And then my interest is to take the scalar product with the vertical direction. And now I introduce just new notation. So I call u dot ez uz. Okay, so this is just uzt minus the derivative in direction z of t. Okay, and now we define a quantity which is the most accepted quantity to measure these heat transport properties, or the enhancement of heat transport. So this is the Nusselt number, and is essentially taking this vertical heat flux and averaging it out. So this, I didn't write it just in a formula, but so this is the average in Z, and so this is written explicitly, and the brackets are horizontal average and also time averages with the fact, so with the extra limit for big time. So I take a long time horizontal average. Okay, so I could have written it, but so you have to understand this Nusselt number really as a statistical average. Okay, so again, we have a long time, so a limb sup for t going to infinity of the average in time, the average in horizontal direction, and the average in the vertical direction. So it's all averaged. Okay, so just to remind you that I will always use this, so a vector x, I will call it x prime for the horizontal direction and z for the vertical directions. Is a notation that I find practical, and I will use it. Now, so what do we expect from the Nusselt number? Well, we expected the Nusselt number, it would be a function of the Rayleigh number, the Prandtl number, and actually also the aspect ratio, because these three numbers are the only non-dimensional numbers of the system. Okay, although the aspect ratio will not really play a role in this bounds, as we will see. Now, the prediction is that the Nusselt number will scale so it will have a power law scaling. So Nusselt number will be Prandtl to some power and Rayleigh to another power. And the idea, the challenge of engineers, physicists, and mathematicians is to actually detect this gamma and beta. At some point, you will see that different numbers will pop up for this gamma and beta. Nevertheless, I want to stress the fact that it's not numerology, but it's more like understanding physical behavior of the fluid, and it will very much change in case of very turbulent flows or steady convection flows. So I must say, so this analysis is very intricate and also fascinating from the regularity standpoint. So there are two main physical scaling. So there are many physical heuristics which predict different scaling behavior. Now here I just talk about two of them, which is probably also the most famous, the argument of Malthus that predicts Nusselt going like really to the 1/3. And this is believed to hold for Prandtl number very big. And it has been observed in experiments. I'm sorry that I didn't put most recent experiments, but definitely we have very, very recent numerical simulation that they observe this Rayleigh to the 1/3 scaling up to Rayleigh of order 10 to the 15. And this is work of Hier, Schill, Schumacher, and Trevisan. The other, a bit controversial physical heuristics come from both Spiegel and Kraichnan independently. They talk about the scaling which is Prandtl to the 1/2, Rayleigh to the 1/2. I will not enter much in this business because it's very complicated, and experiments and numerical simulation don't reach this scaling, so they don't observe it. Although the physical heuristics are quite convincing and use the so-called free fall acceleration and as a rate limiting factor that transport in the bulk. But nevertheless, I will not go into detail, just to have a picture of how things are intricated. I reported this this paper, so this picture from a paper of Allers, Grossman, and Lose. So there is a big group of physicists in the Netherlands that are working on the Rayleigh-Bénard convection problem, and they try to unify a little bit the theory. And they, in a phase space of Rayleigh-Prandtl, they try to tell you in each region which scaling you will have. Not everyone agrees on this, so these lines in this log-log plot that are not, we don't know whether they are the correct one, but nevertheless, it was a nice attempt. And okay. Now, because Malgo's argument, in fact, will motivate what I will tell you in starting from the next slide. So let me tell you that for where does it come from? Very, in a sense, also leaving a little bit of detail just to give you an idea. So he believes in the Rayleigh 1/3, or he gives us an argument for the Rayleigh 1/3 scaling. So this comes from the fact that transfer of heat across the boundary layers into the bulk is seen by him as a rate limiting process. So because the major temperature drop happens to be in a boundary layers of size delta, so he's really focusing on the boundary layers, he says, okay, the Nusselt number in a boundary layer should go like 1/delta. Now, he uses the stability, so the linear stability argument that predicts the existence of a critical Rayleigh number under which the dynamics are trivial, so there is pure conduction, and over which you start to develop convection and then turbulent. So essentially the Rayleigh critical is detecting the first bifurcation of the system. So he says, okay, my boundary layer wants to be just about stable, really in the sense of the stability analysis. And then by this idea that the boundary layer as a layer itself wants to be borderline stable, then he, by this simple computation, which you just plug into the Rayleigh number, the new height, which is delta H, you will see that there is a relation of the type Rayleigh critical equal 1/2 Rayleigh delta cube. Okay, and then since the Rayleigh number is supposed to be a universal number, then and it's not supposed to be, there is actually a proof that is a number. Then delta, if you invert this relation, it would be raised to the -1/3. So this then plugging in Nusselt goes like 1/delta, you see that the Nusselt goes like really to the 1/3, pops up uniformly in Prandtl. Okay, and it's based on this boundary layer that wants to be marginally stable or just borderline stable. Okay, so now we enter a little bit in the, I have to have an eye on the time. We enter a little bit into the analysis. For this talk, I would need two a priori bounds. So one is for the energy of the Navier-Stokes equation. So here I write that there is an energy inequality for Leray solution, and it looks like this. And this is formally just an integration by part. Nevertheless, in the case of, so in 2D dynamics, as I will describe later, here we have an equality, okay? And otherwise, we have an energy identity for the Nusselt number. Again, this is based on an integration by parts. Then the Nusselt number is the average of the Dirichlet energy of T, big T. Okay. So if we remember these two properties, because these are, or connection between the Nusselt number and the grad of T and the grad of U, this will be important in the future. Okay, now in order to start a little bit of these remarks on the boundary condition, let me go introduce you very quickly a method that is called the background field method, introduced in the 90s by Doering and Konstantin for this specific problem. So this method is based on decomposing the temperature as a background profile tau, depending on only the variable z and the fluctuations. Now, so this tau profile is a profile that is inheriting the boundary condition from the temperature. So is 1 in 0 and 0 in 1. And then there will be fluctuation that satisfies homogeneous boundary condition and this equation, which is the equation for the fluctuation coming from the equation from the temperature. Now, the Nusselt number, as I told you in the previous slide, is this the average of grad t squared. Now, if we impose the decomposition, we get these three terms. And now the idea is to use the energy balances we have. So one is for theta and the other one is for u. Again, we are doing formal integration by part for u. Then taking the long time averages of these two balances and combine them, we see that we find a relation. So we find an identity for this term. Yes?
I'm sorry, there's a question on the chat. Can you show again page 9, please?
Page 9, yes. Laura, I cannot see the chat unless I go out of the screen.
Okay, no, Leonardo De Carlo just says, can you show again page 9, please?
Yeah.
So, okay, thanks.
Okay. Okay, grazie, Laura. So what I was trying to say is that, so you see that now, because of these balances, I can rewrite this identity, which is expressing tau prime dz theta average, and then putting back into this representation of the Nusselt number. Okay, so so remember these two balances and the fact that we use these two balances. Then we rewrite the Nusselt number by just simple manipulation as tau prime squared. So this is the energy of the integral of the slope of the profile squared minus a quadratic form. And this quadratic form is encoding all these terms that we have seen here. Okay, the tau prime square was also here. So this is the energy of the background profile. Okay, now we have a criterion. So if this quadratic form is non-negative for all theta, then the Nusselt number is bounded by the Dirichlet energy of tau. Okay, so this is now the criterion, and it's very simple, and I want to show you just one example to apply this criterion. By the way, so this arguing really comes from this Malthus type of approach, in which he says that the rate limiting process is this heat transport from the boundary layer to the bulk and not the other way around. So example, let's choose a tau that has this shape. So it's laminar, so linearly decreasing from 1 to 0 in this boundary layer size delta, then is increasing in the bulk, and then again decreasing to match the boundary condition again. So this, as you remember the talk of Michele Dolce yesterday, so this is a stably stratified profile, as the lighter, warmer parcels are on the bottom of the colder parcel. Now the question that we are asking is this marginally stable, meaning is the quadratic form non-negative? And now, so the argument is very simple. So the tau now has a shape, we put it in this representation, we get these two integrals, but now understanding this integral between 0 and delta of uz theta is very easy. Why is very easy? Because we have that theta is equal 0 at the bottom, and also the vertical velocity is 0 at the bottom. So this is, or let me put it like this, if UZ is equal 0 at the bottom, what you can do is to apply the Poincaré estimate, and so that you can relate this UZ theta to dz theta squared average and dz UZ squared average. So this is, again, is just applying Cauchy-Schwarz and Poincaré estimate, both in theta and UZ, with the assumption that UZ is equal 0 at the boundary. Now, this is a very simple estimate that then you can put back into this quadratic form here to estimate it. Remember that we want to show that the quadratic form is non-negative. And then, so the condition that ensures us that the quadratic form is non-negative is that this parenthesis here is non-negative. So in particular, this tells us that if delta is of order radius to the -1/2, then the Nusselt number is bounded by radius to the 1/2. Okay, so this is a very simple argument that essentially uses only the Poincaré estimate and the Cauchy-Schwarz inequality that shows us this very directly this bound radius to 1/2. Now, the only thing I was using here is that UZ is equal 0 at the boundary. So meaning that the vertical component of the velocity is 0 at the boundary, but I'm not using anything else. So can we do better? Well, this is what I'm trying to tell you today, that one can do better, and exploiting more information about what happens at the boundary. So in particular, I didn't yet describe what boundary condition I'm willing to use, but nevertheless, you will see that in the condition that I would describe, UZ would be equal 0 at the bottom, and then I will implement it with more condition on either on the horizontal part of the velocity. Nevertheless, before starting with this, I want to tell you that this is a meaningful research. Why? So because trying to understand the role of the boundary condition in turbulent transport and whether they play a role is something that for which Charlie Doering has spent I think a very good part of his scientific career, and also with a lot of debate with the physicists, because physicists have, or especially a group of physicists in the Netherlands, were trying to convince that in fact the Rayleigh to the 1/2 scaling for the Nusselt number was the actual ultimate scaling. And this is something that obviously is would mean that in this argument you are not using the full set of boundary conditions. And so this is a debate that has been going on for a long time, and in particular I'm just showing you a discussion that happened on Physical Review letter between Charlie Doering and Cotters and this other group in the Netherlands, in which Charlie was telling why we cannot conclude that Rayleigh to the 1/2 is the right scaling. The classical, okay, now I tell you a bit more. So the classical Rayleigh-Banach convection problem is complemented by the no-slip boundary condition. So besides UZ equals 0 at the boundary, you will put also the horizontal part of the velocity equals 0 at the boundary. Now, I don't enter in detail. Many people, and also many people in the audience, have worked on this problem. And here I'm just reporting the best up-to-date bounds that are known in the case of finite Prandtl. And so just with the observation that the Rayleigh 1/2 uniformly Prandtl bound that was proved by Doering and Constantin in '96 seems to be a bit better than this newer bound by Chauffroux, myself, and Otto, in which, at least in the region of very small Prandtl number. I will not enter in detail. So it's very interesting, but because of time, I have to move into some consideration. So what moved me from searching something different or exploring other type of boundary condition for this problem was coming in a big part from Charlie, and then I've been looking around trying to understand what other founder of fluid mechanics thought about it, and I found this sentence from Serrin in the book Mathematical Principle of Classical Fluid Mechanics in '59, in which he said, well, Stokes argued that the fluid must adhere to the solid, since the contrary assumption implies an infinitely greater resistance to the sliding of one portion of fluid past another than to the sliding of a fluid over a solid. But although these facts are quite convincing, when moderate pressures and low surface stresses are involved, they do not apply in all cases. In fact, he cites two instances for which this the no-slip boundary condition don't work. So it makes sense then to look at other type of boundary condition. In particular, for example, Charlie, together with Gerard Whitehead in 2011, they start exploring free slip boundary condition. In particular, if I think about a very, very old first study of Lord Rayleigh on the Rayleigh-Banach convection problem, he also was using the free boundary conditions. So the free boundary condition, again, UZ is equal 0 up and down, so at the boundary, but here we have that the vertical component of U prime is equal 0. So we don't have U prime equal 0, but the derivative in the vertical direction of U prime is equal 0. These two conditions together are telling us that the vorticity in 2D is equal 0 for this problem. And the Whitehead and Doering for this problem show us that Nusselt is bounded by Rayleigh to the phi over 12 with some implication. But before coming to the implication, let me tell you what is their idea, because their idea is in fact very, so in this argument, they don't lose at any point. So this is what I want to tell you. So first of all, they maximize on the number of balances. If before we were looking only at the balances for theta and u, now they have an extra balance identity that they can use, and it's the one for the vorticity. Remember, the vorticity is equal 0 at the boundary because of the nature of these free slip boundary conditions. Then with skipping details, which are less interesting, so let me, so they write down the Nusselt number in this form. Again, there is the integral of tau prime square minus a quadratic form. And this quadratic form looks pretty much like the one we were seeing before. Before we were seeing this guy, the grad of theta squared, the mixed product, and also this guy that we were writing as grad of u squared. The rest is new. Now, the second important part of this approach and the crucial observation is that they can estimate the mixed term in a very smart way. And this very smart way is to estimate the UZ and theta in terms of omega and the derivative of theta. Now I'm passing Fourier transform. And why I did it? Because the argument comes out a little bit more in its original formulation, because they formulated like this, but also one sees the argument a little bit better than if we would not use Fourier transform. Nevertheless, the choice of the tau, which I didn't mention, but here they are really using something which is constant in the bulk so that they can eliminate the whole, so tau prime is equal 0 at the bulk, so they can eliminate the whole part between delta and 1 minus delta. So just one slide to tell you how they did it, because I think that it's very nice to see that this bound is extremely smart. So they look at the pointwise at a pointwise estimate for u, the vertical component of u by using the fundamental theorem of calculus. And in particular, they relate, since this UZ in 0 is equal 0, then they relate UZ with the L2 norm, and that paying Z to the 1/2. Now they say, since we have this boundary condition, UZ is equal 0 at the boundary, then we have that the derivative is mean free. So in particular, there exists a point wherever it lies in 0, 1, such that the derivative at this point is 0. And now they use exactly this fact to just reapply the fundamental theorem of calculus for finding a pointwise bound for this guy. So the derivative of UZ squared. And now by interpolation, they relate this guy to, I mean, it's also written here. So it's the second derivative of UZ and the first derivative of UZ, smuggling in K, so frequencies. And eventually by so a certain choice of C1 and C2, this whole term can be bounded by K times omega in L2. And this is exactly what I have been writing here. The argument for theta is essentially a very simplified variation of this argument that I gave you. So this was the sketch of the very smart estimate of Charlie and Jared. And but we want to even move forward with this analysis on the boundary condition, because the problem of the free sleep boundary condition is that they are not really physical boundary condition, meaning that the vorticity is zero at the boundary, so there is no production of vorticity at the boundary. So this is regarded as non-physical. And then there is a second point. In reality, few surfaces are either no sleep or free sleep. So in particular, I found by trying to understand this business, I found this interesting paper in which Zhu and Granich say, well, there is no compelling argument to justify the standard no-sleep boundary condition of textbook continuum hydrodynamics. However, this assumption successfully describes much of everyday experience, and then he cites Feynman. But then he says, well, Feynman noted in his lecture that the no-sleep condition explains why large particles are easy to remove by blowing past a surface, but small particles are not. And they say, well, readers who wash dishes have noticed that it's difficult to remove all the soap just by running water, and a dishcloth is needed for effective cleaning. So what are they trying to tell us? Which is very reasonable to consider surfaces for which some sleep occurs. And in particular, they are telling us something about the roughness, so the roughness plays a role in everyday life, in all surfaces, okay? So, and this motivated us to look first at a simplified version of the Navier-Stokes boundary condition. This Navier-Stokes boundary condition deviates from the free sleep boundary condition because the right-hand side now is non-zero here. So the dz u prime is non-zero, but it's u prime times 1 over ls, where ls is a sleep length, positive. Okay, still we are not looking at roughness, so the boundary are flats, but we allow some sleep, which we were not allowing before. So now we expect that this boundary condition will this boundary condition can be seen as an interpolation between no sleep boundary condition and free sleep boundary condition. So we also expect that the results will interpolate between these two. And now I'm entering the last part of my talk, in which I tell you that recently with Theo Drivas and Huy Nguyen, we have been looking at this problem, and in fact show that also the bounds interpolate between the 5/12 bounds of Döring and Whitehead and the 1/2 bound from Döring and Constantine. So we found this interpolation I want to tell you that, okay, so for slip length approaching infinity, clearly this reduces to the Rayleigh 5/12 bounds in agreement with the free stress bound of Döring and Whitehead. Okay, so just a couple of slides to tell you what the main trick or the main argument here is, which is new compared to previous result. Well, here again, inspired by the work of Charlie and Jared Whitehead, we were looking at the vorticity and the equation that the vorticity satisfies. Now, when we are going to look at the balances, now, obviously at the boundary, we produce stuff. And in particular, so from B, this is the energy estimate that gives us these extra terms. And then in A, we have from the vorticity estimates, so for the vorticity balance, we produce new terms that, interestingly, involve the pressure. So it's not surprising, but the fact that the pressure enters this analysis is new, because with no slip and free slip, the pressure has never entered this estimate, or at least not in this very spontaneous way. Let me put it like this. Okay, so then again, using the same tricks, so we rewrite the Nusselt number together with these new balances. So the argument, at least philosophically, is very similar to the one of Döring and Jarrett. So we build up this new Nusselt number, which is 1/2 delta. This is again, depending on our choice of tau prime, which is really localized at the boundary, plus this certain m parameter times Rayleigh squared minus a quadratic form. And then now I want to show you the quadratic form, because the quadratic form looks much more intricate than before. And let me just tell you that there will be 3 terms, grad theta average, grad theta square average, omega square average, and grad omega square average, that I call the pivot terms. So these are the terms that now have to be my pivot. So I have to really try to connect all the other terms to these three terms. So then we have a mixed term on the second line, and this we treat it like Döring and Jarrett, in the sense on the same type of tricks that I was telling you about. But in this analysis, we will get rid of completely of the Fourier transform techniques, which are not needed. This term that comes from the energy estimate, we throw it away because it's positive. So remember that we want to show the quadratic form is non-negative, so this we throw it away. And now there is, the last term is okay by Cauchy-Schwarz, because you see that there is omega and the derivative of theta. So omega is here, the derivative of theta is here, so just by Cauchy-Schwarz, this would be more or less okay. But this part involved in the pressure is new. And this was the main effort of understanding how to bound this stuff, especially the pressure at the boundary, which is nasty. Generally the pressure at the boundary is large. So the way we did it is by tracing back the pressure, in especially, so the pressure satisfying an elliptic problem, we all know, but we had to trace back what it does at the boundary. So in particular, we traced the dz p at the boundary to build up this problem. And in particular, using the trace estimate together with a careful estimates on the H1 norm of the pressure that gives us this upper bound here. So this will give us, this is essentially telling us that so this is the main trick. So obviously I'm not giving you the full detail. What I want to tell you is that if you see the right hand side here, besides the gradient of omega and t in L2, we have an omega in L2, but also omega in LP. So in particular here, trying to imitate some bounds of Lopez planas for that were derived in order to look at implicit limits of Navier-Stokes equation with the friction. So imitating this type of arguments, we find that a uniform mean time bounds for omega in LP. And this obviously grants us a bound for this guy on the right hand side of the pressure estimate. And in particular, just as a side remark, this estimate is fundamental also because here, I didn't tell you, but here there would be the derivative of omega in L2 that somehow we have to get rid of. And so here we showed that this, so the uniformly omega in LP is bounded. So especially when you take long time limits of the time derivative of omega in L2, this will not create any problem. So all in all, just to conclude, you see the pivot terms, this one, and this one, and now all the other terms have been put into this into this form, so that you see now we have to optimize on the what's in front of grad of omega in L2. And also we have this big parenthesis, which is obviously much more tricky to optimize, but nevertheless one can do it. And by a certain choice of A, B, and we have different balancing parameter and delta, you see that delta comes out again, is delta scales like really to the -5/12. We can show that Q tau is non-negative. In particular, this will give us this bound in which we see clearly the interpolation between the Rayleigh 5/12 and the Rayleigh 1/2 multiplied by L to the -2 that has to be there, because in fact, if L goes to infinity, if the slip length goes to infinity, we have to go back to the result for free slip. So it means that this result is consistent. The last slide is to tell you that in this 2D picture, or in these two, so in these bounds that I told you in 2D, what can we extrapolate? Well, we can extrapolate the fact that free slip boundary conditions seem to enhance heat transport compared to no slip. And then the last observation is that if we set so we make a specific choice of slip length depending on the Rayleigh number to the power alpha, we can rewrite the bound. So this bound here, we make a specific choice of LS, so we take it to Rayleigh to the power alpha, and we deduce this upper bound. So for alpha bigger or equal than 1/24, we have Rayleigh to the 5/12, and for alpha smaller, we have Rayleigh to the 1/2 - 2 alpha. Now, what is the observation here is that for small slip length, this bound is actually better than the one of Doering and Constantine 92. And in particular, this is telling us that the Navier slip conditions seem to inhibit turbulent transport compared to no slip, provided that we have this, we are in this region. So LS is bigger than Rayleigh to the 3/4. Now, the last observation is, why do I see SIM 2? So these are upper bounds. We don't know yet if these upper bounds are attained. This is a very difficult business. Lower bounds are not there. So what we can try to do is always trying to optimize on upper bounds. And another question that another important points that I didn't touch today is that this is really an interplay between mathematics analysis and numerical simulation and experiments. So sometimes, let me put it like this, as as a consistency check, or in order to check that this bound might or be optimal, you would compare it to what the numerical simulation suggests, or what the experiment. The experiment is a little bit more tricky, but let me put it like this. Numerical simulation generally are giving you at least for large, but not asymptotically, they will give you a behavior of the scaling law. So in a sense, at the moment we cannot find lower bounds, but definitely there are supporting evidence from numerical simulation that these bounds might be optimal. Now, can we actually prove this optimality? Do I believe in the future we can show lower bounds? This is, I don't know, that would be very interesting, maybe with a big reduction on the in the modes of these problems. Maybe we can do something for simplified problem, but for the full system, I find it hard, but nevertheless, we hope that there will be something in this direction soon. Okay, thank you for your attention.
Thank you, Camilla, very much for a very nice talk. Is there any question or comment? So I don't see any. I have a couple of comments. So two are sort of historical remark. Well, one is a historical remark that actually Navier condition are called like that because they are the ones that are already present in some ways in Navier work on the Navier-Stokes equations. Mm-hmm. You know, and there is also work by Michelic and Robert, I think it's in the 90s, in where they actually show that if you homogenize the no-slip boundary condition for a highly oscillating boundaries, you actually get Navier boundary conditions. Mm-hmm. The sort of common question is that with Navier boundary condition, you can pass to the zero viscosity limit, particularly in a channel, which is your setup. So I wonder if people have thought to maybe try to combine to see what happens to these bounds as you send viscosity to zero, which you couldn't do for, you know, for no slip. We don't know how to do it for no slip boundary conditions, but you can do it with Navier.
Yeah, so this brings me back to this work of Elena Lopez and Planas, in which they actually did this type of
yeah, and there's been many developments since then, actually.
Yeah, definitely. So for me, I must say, is a rather new topic. So this type of boundary condition, but I've seen that definitely Elena and people around her have worked already with the friction at the boundary. And actually, so now I forgot another important reference that was given there, and I actually used to look at this paper, but at the moment I missed the names. But definitely there is so in 2D.
Mm-hmm.
In 2D there is already quite a number of results in this direction.
Okay.
Yeah, so unfortunately, I forgot. There was a breakout result. Okay, maybe I can tell you later. So it's a famous paper in this context. Yeah, so this is an interesting problem, nevertheless. Yeah.
Because you have two different boundary layers, the one coming from convection, the one coming from the viscosity. So I think
so this is a tricky business. So okay, now I reconnect to what you were asking me. So this is Anna, this is a bit difficult because as you see from these bounds here, so the only boundary layer that I have is a thermal boundary layer, but not a viscous one.
Yeah, I understand that, but yes, I'm just saying that maybe one could attempt first to just obtain some bounds, okay? That are uniform in viscosity, and then in the second step try to see one can study the interaction between the layers.
It's a very good observation. Yeah, absolutely. Yeah.
Camilla?
Yes.
Hi. When you say that you only see the thermal boundary layer, since you're using background field method, you also have to choose a background for the velocity, right?
No. No. I'm not using a background flow for the velocity. It's just for theta, so for t.
Ah, okay.
No. I mean, this would be interesting, Christian. This is something that one has to do at some point to encode this viscous boundary layer. But it's a very important question, but I didn't do it. So here, all the analysis is with that one boundary layer, which is thermal.
Okay, thanks.
Other comments or questions? I don't see any. So let's thank Camilla again for the very nice talk.
Welcome everybody to this afternoon session. The first speaker is Didier Bresch from the University of Savoy-Mont Blanc, and he will speak about Hopf solutions for compressible Navier-Stokes equation. So, please.
So thank you very much. So first, I want to thank Giovanni, Gianluca, Anna, Laura, and Stefano for the organization. Even if we are with Visio, it's not so good, but we can learn mathematics, so it's good. So I will talk about Hopf solution today for compressible Navier-Stokes equation. And this is based on a joint work with Cosmin Burtea, who is in Paris, actually. So he has a position in Paris. So as I said, I will talk first so compressible Navier-Stokes equation, and I will also discuss a kind of solution which is well known in compressible Navier-Stokes framework. And the kind of solution is named the Hopf solution, but I will explain why, well, what it is for people who don't know. So the first thing that I will do is to introduce people who don't know on a non-stationary compressible Navier-Stokes equation. So for the non-stationary compressible Navier-Stokes equation, what is really important is that first you have an equation on the mass, but the velocity is not given. The velocity solves a momentum equation, which is a parabolic equation, which is this one. And in this parabolic equation, you have several terms, which are really important in the next slides. First, you have a total time derivative, which is the total time derivative in the momentum equation. You have the gradient of a pressure, but the pressure is given in terms of rho. It's a function that you have to give in terms of rho, so I will say more later. And something which are really important from a physical and mathematical point of view is the diffusion term that you will put in these equations. So what you can say is that in fact you have an hyperbolic, parabolic system, and what you want to do is to see what you are able to say from a well-Posnet's point of view for this system, which is fully nonlinear, and is nonlinear in terms of the velocity, looking at this one, but in terms of the pressure also, if you assume a nonlinear function for the pressure. So the thing which is really important is to discuss the diffusion, because from a mathematical point of view, usually when we talk about diffusion, we think about constant viscosity and the Laplacian. That means the classical one that you can see in mathematics is this one. So you have two coefficients, which is lambda. Lambda is the bulk viscosity, which encode in fact the compression, and the mu, which is the shear viscosity, which encode the shear of the flow. So you can put a Laplacian if you want from a mathematical point of view and don't care about the last one. But what is important is that in mathematics, usually you see this system. Of course, you can have more complex diffusive term. One is if you assume, for instance, the viscosities, the two viscosities, mu and lambda, if you assume that they are not constant, and if they depend, for instance, on the density, then you can have a viscosity which is as this one. That means a viscosity which depends on rho in the two parts. The part which is the compression part, that means which encode the divergence of U, and the part which encodes the shear stress, which is the mu rho. I will not discuss about this case today. I will talk about viscosity, which does not depend on density. That means viscosity could depend on the time and space, but as a given function. So in physics, if you look at, for instance, geophysics, the viscosity usually is not an isotropic viscosity. By isotropic, what I mean that you see the viscosity mu is the same in front of all the derivative for the Laplacian. That means if you have, for instance, 3 variable x, y, and z, if you put mu the same for dz square, dx square, or dy square, this is what we call isotropic. And if you allow mu to different viscosity in front of the partial derivative, that means that you want to consider an isotropy. And this is important because it encodes that you can have different diffusion depending on the space variable. So if I want to talk about that, I can write the diffusion as a diffusive term, a divergence of a matrix. So it's a tensor here. You see the A tilde, this is this one, the big one here. A tilde is a tensor, and this tensor may depend on time and x, and could be given with respect to time and x, or even constant if you want. But the coefficient may be different depending on the index that you choose, A, G, K, or L. Of course, if you have some value for these coefficients, which give you exactly the constant one. So the initial data for this system, you need to put an initial data for the density, of course, and you need also to put an initial data on rho u. So this is what I put here. I don't talk about bounded domain. I will assume to have a periodic domain to don't care about behavior at infinity or boundary condition for bounded domain. So let's just think about torus media and look at this system. And what I want to discuss about such kind of diffusion, which is an anisotropic diffusion. Okay, so let me give you some comments first for people who don't know really on compressible Navier-Stokes equation. So as I said, you see that so the viscosity, the coefficient, the anisotropic coefficients may depend on t and x. The function p, the pressure, is given. That means you give me the function, the pressure function. And the viscous term d may be more general than what I wrote before. And this is exactly the message that I want to share with you. The fact that compressible Navier-Stokes equation is far to be solved for a weak solution on a weak regularity. So for compressible Navier-Stokes equation, I just write very simple thing. That means that if you look at literature, you can find various kind of solution, starting from the weakest one from a regularity point of view, which is the dissipative solution, going to the more regular one, which is the classical or HS regularity solution. When you have a regular solution, you ask for regularity for the density and the velocity. For the two, the density and the velocity also. In between, you have the weak solution à la Leray. That means exactly the same in the same frame than the incompressible Navier-Stokes equation weak solution. You have critical solution. So for compressible Navier-Stokes equation, the good reference, according to me, is Raphaël Danchin, who has worked a lot on compressible Navier-Stokes equation in critical space. But if you have in between, so the weak solution, which is the one that I talked about, but in between, you have intermediate solution, a la Hopf, the Hopf solution. And what means Hopf solution? So you have two unknowns. You have the density and the velocity. So Hopf solution is when you want to assume not too much on the density. That means only, for instance, L infinity bound on the density. That means that you want to allow interfaces. You want to allow to have some mixture. You want that the density to be not regular, but the velocity could be regular, a little bit regular, in order to be able to track information around the flow. That means that you want to see if your system may give you some solution which is only L infinity in density, and on velocity a little bit more than the usual information given by the energy. And for instance, assuming that looking at if you can have a velocity which is h1, for instance, in space. So L infinity for the density, h1 in space, and are you able to show me a global a kind of global existence for this system? And this has been done by Hopf in the middle of the 80s, and I will talk about that, and I will give you how he succeeded to do it, and I will comment some models that are not which was not able to be considered with the technique by Hopf, and how we succeed to extend it with Cosmin Burtea to fix it. So just a remark, for incompressible but non-homogeneous Navier-Stokes equation, that means you take the usual Navier-Stokes equation, but you add a density in the system. That means that you have a transport equation with a density. Now the velocity is divergence free, and you want to be able to look at a density which is not regular, that means which allows some interfaces, and with a little bit of more regularity, but with a little bit of regularity on the velocity. You can see a lot of recent works by Raphaël Danchin, Mucha, Chemin, Zhang, and others. I will not enter in details. And they extend this Hopf-type solution for the incompressible non-homogeneous Navier-Stokes equation. So this is something really interesting. And so let me first talk about, in the first part, of weak solution. And after I will switch on the Hopf solution in order to understand in a precise way what is the difference between the two. So first, let me recall, but people know a lot in this workshop. That means that we all know the paper by Jean Leray sur le mouvement d'un fluide visqueux remplissant l'espace, where in Acta Matematica, where he constructed a smooth solution up to a characterized existence time, and also he introduced the concept of weak solution that he named turbulent solution. And for this weak solution, few information on the well-posedness is obtained, because such study you have few information, that means no more. Not a lot of regularity result, no uniqueness at all, but there is a real interest from a particle point of view. The first one is that the stability property for weak solution help a lot to approximate a stable numerical scheme. So this has been done, for instance, by several groups, as Edouard Feiergel, Thierry Galouet, and others. They really use the theoretical development of global existence of weak solution to develop stable code. And this also helps you to better understand the structure of the equation, because as you ask not too much on the regularity, you need really to play with the equation and to look at what are the main ingredients which are conserved in order to preserve the stability. So mathematically, you can find some important physical quantities in the system. So now I give you a general things well known by everybody. That means that if you want to show global weak solution à la Leray, you need first to have a priori estimate on smooth enough solution. And after, you need, of course, to construct these regular solutions. and to show that these a priori estimate are satisfied uniformly, and then pass to the limit and use a compactness argument to show the convergence to a weak solution. So the main difficulty is that the real nonlinearity of the compressible Navier-Stokes equation, because as I said, you have the pressure, which is nonlinear, and you have also the quadratic term for the velocity, but the most difficult one is the pressure. So let me give you a first and important remark. So for weak solution, assume that for incompressible Navier-Stokes equation, I ask you to change this guy, that means the usual Laplacian that you put in the Navier-Stokes equation, by another one, which is an anisotropic viscosity. So you see, in the x variable, so x will be the horizontal and z the vertical. Then in the horizontal components, I put a mu x, and in the vertical one, I put a mu z, and I assume that mu x is different from mu z. And I said, I ask you, are you able to show the same that has been proved by Euler for global weak solution for incompressible Navier-Stokes equation? And everybody will say me, of course, because you do not change the parabolic feature of this system if you assume the viscosity to be far from zero. So you have this parabolicity, you have this H1 regularity, which does not change, and that means that you have, without work, the same conclusion. But for compressible Navier-Stokes equation, what I want really to insist on is that if you put an isotropic viscosity or an anisotropic viscosity, this is really not the same. That means anisotropic viscosity is really more complicated and is actually an open problem in its full generality. That means if you assume mu x different from mu z without assumption between mu x and mu z, this is an open problem. Something has been done with Pierre-Emmanuel Jabin, and I will explain you later on. But in the full generality, it's an open problem. So I hope at the end that you will understand why. So what are the difficulties in the compressible setting? So first, it is because you have weak bond on the divergence of the velocity. Because if you are weak solution, the only thing that you know is that U will be in L2H1. That means the divergence is no more than L2. So the velocity is not a given function, is linked to the density using the momentum equation. That means you do not ask something on the velocity. You have to play with the momentum equation to link the velocity to the density and to go back to the equation on the density. For weak solution also, since the velocity is not regular, you can have very bad behavior of the density, such as oscillation, concentration, and also possible degeneracy, that means vacuum state, that means ρ may vanish. You can also have possible non-local properties. I will discuss that later on, and this is really important. For instance, if you assume to have a non-constant, a non-isotropic viscosity, that means mu x different from mu z, you will see that you have non-local properties, which is not so good. So you need really to focus on the use of the structure of the system and try to see what happens. So what I want just to communicate on is that you have the momentum equation, which seems to be really complicated to deal with when we start on the compressible Navier-Stokes equation. So what I said, forget about the momentum equation and just assume that you have a velocity field, which is L2H1, for instance, which satisfies a constraint on the divergence. That means divergence U is almost P-ρ plus some compact term in space. So you don't care. That means divergence U is almost P-ρ. So what you see in this relation that I write just by hand is that divergence U minus P-ρ is compact, but divergence U is almost P-ρ. So for the usual barotropic Navier-Stokes equation, this is exactly what is strongly used to prove global existence of weak solution. It's the fact that the divergence of the velocity is almost P-ρ in terms of compactness. If you use an anisotropic viscosity, then you will have almost this relation, but with one thing which change, you have an operator in front of P rho, which will be an order 0 non-local operator. So this is really important because instead to have a pointwise relation between divergence U and P rho, here you have an order 0 operator which link divergence U and P rho, and this is the main problem to prove global existence with anisotropic viscosity in the general form. So for the weak solution, so I just remind for people what is known. So if you have the mass equation with the momentum equation, so in the momentum equation, as I said before, you have the diffusion. Then what was known before 2015 is if you assume the viscosity all the time constant, so you see all the time you have the viscosity constant in all this work. So if you take a pressure which is a power law, so here it's the same, it is a power law, then you have global weak solution. If gamma is bigger than 3d over d plus 2 for Lyons, gamma bigger than d over 2, which is an improvement by Fayergel, Novotny, and Petzeltova, or more generally, and you see here, you can relax a little bit this monotonicity, choosing to have only a monotonicity after a certain value. Okay, because if rho is bigger than a certain constant, then you see that P prime will be positive, and you will have a monotonicity as property of the pressure, which will be strongly used to prove the global weak solution. And there is another paper, which is an interesting one, which gives the global weak solution in the critical number, which is d over 2, which is by Plotnikov and Vegan in Saya. But what is important to see is that in all these calculations, you have the constant viscosity, and you have also the monotonicity of the pressure, at least after some fixed value. So let me just give you the comment to explain why it is like that. As I said, the main step in the proof is the energy estimate, as usually. And after you want extra integrability of the pressure. So I don't enter in the detail, but have just this in mind. You want more information on the pressure, integrability on the pressure, in order to be able to pass to the limit in the pressure itself at the end. And what you use is exactly what I said before, the fact that divergence U is almost P rho in terms of compactness in space. And how it works to use that is the fact that in the mass equation, you can pass to the limit, all the terms are compact, you can write a renormalization equation. So you pass to the limit in the mass equation and you look at what is satisfied by rho log rho. You see for a renormalization solution that it satisfies this equation. You can also write this equation for a fixed parameter epsilon, which is the sequence, and pass to the limit in this system, which gives you this one, where bar means only mean velocity, mean weak limit on the system. And if you want to prove compactness on the density, you need only to show that this guy is exactly the same than this one. That means the weak limit of the nonlinearity is the nonlinearity of the weak limit because of the property of the S log S function. So if you are able to show that, you will have the compactness. And to show that, you see that if I want to have a comparison between this guy and this guy, I will need to compare this guy to this guy. But to compare this guy to this guy, I can use this. If I use this, that means that I can change divergence U by P rho, or the weak limit of P rho. That means this guy minus this guy may be written in terms of rho itself, without velocity inside. It will give me a term, which is a complicated term, as rho P rho bar minus rho P rho bar. Okay, so this is now just to look at what is the property of the pressure, and is it possible to have a sign of this guy? And if it is the good sign, it will give me the equality of this guy and will give me compactness. So just have in mind, I don't give you the details, but have in mind that what is really set, which in the frame, really, the key in the proof is the fact that divergence U is almost P-rho. That means that divergence U minus P-rho is compact in space in order to change the view by P-rho at some point and to use pointwise property to compare and to characterize the defect measure. But this does not work for anisotropic viscosity, because for anisotropic viscosity, as I said before, this guy is not this guy. So this weak solution has been studied with Pierre-Emmanuel Jabin. And what we succeeded to do is two things. We can assume to have a pressure which is non-monotone. So you see, the pressure is just in between 2 power gamma of rho. And you just ask to have a control of the derivative of P. So this is one thing that you can do using a constant viscosity diffusion. Or you can also fix the pressure. That means assume that the pressure is a power law and just play with the anisotropic viscosity. And this is what it is important for you. Forget about the first, but have this in mind. We are able to treat a diffusion which is not a constant one. So that means we change a little bit the identity. So you have an identity plus some add-in matrix, a tensor. On this tensor, you just assume you just have some assumption on this tensor. You see that it depends only on time and not on x. This is for simplicity for proof, and because it's more complicated, really more complicated if you put an x inside. And you have a constraint on gamma. So gamma is the power, has to be strictly bigger than some constant depending on the dimension. And the anisotropy has to be controlled in terms of the viscosity mu on lambda. So mu is here and lambda is here. So that means if I assume lambda, so as I said to you, which is the viscous compression, the bulk viscosity large, if the bulk viscosity is really large, then I can take anisotropy large. Okay, so it depends on the size of these two guys, of this quantity, which will say you what kind of anisotropy you can use. So to do so, we do not use the rho-log-rho trick, but with Pierre-Emmanuel Jabin. So we develop, we look at a propagation of some quantity, which is this one, but with appropriate weight in front of. And this weight is a dynamic weight satisfying some PDE. And we discuss a little bit about that. And this is the result that we get. But I don't want to talk about this result today, but just to have in mind that for global weak solution, we are able to have global weak solution for anisotropy, but with some constraint on the anisotropy and with some constraint on gamma, if P-rho is rho gamma, or a non-monotone pressure law if you assume constant viscosity. So what I want now to talk about, and it is the main topic for the talk, is the solutions à la Hopf of solution on compressible Navier-Stokes equation. So as I said, Hopf solution is a notion between strong solution and weak solution à la Leray. What I want, and what David Hopf wanted in the past, is to allow discontinuous density, assuming extra regularity on the velocity field. That means not only the L2 bond, which is assumed for the weak solution. Usually for the weak solution, square root of rho 0 u0 square has to be integrable. But in a Hopf solution, you assume a little bit on this velocity, and you want to show that there exists a solution for which the density will be bounded. So, for instance, if I assume u0 to be in H1, I will have a very nice property in order to follow information on the density. And this will be really interesting from a quantitative point of view in order, for instance, to study the dynamics of surface of discontinuity that you assume initially. This has been done, for instance, by David Hopf in some very nice papers. One, for instance, in a bounded domain, when you have interface with a cusp close to the boundary, and you want to see what happened on this cusp when the time is just after 0, and you can show some changement of instantaneous change of this interface and of the topology of the cusp. And you can also use the fact that you can follow the interface in order to study a mixture, for instance, a multi-fluid system. And there is, for instance, recent works that we have done with the group, with Burtea, Mathieu Hilleret, who is in Montpellier, Lagoutière in Lyon, and Xiangli Huang in China. That means that if you use the Hopf solution, so L infinity initial density and H1 initial velocity, then you can assume initially to have a kind of fast oscillation of your L infinity initial density and try to look at for some specific initial data if you are able to perform some kind of homogenization. And what you find that you can justify mixture models which are used in physics, but with real physical relaxation term and linked to the viscosity. So this slide is just to say you that Hopf solution is really used to look at quantitative properties of uncompressible Navier-Stokes equation. So let me explain you the ideas by Hopf to show a solution regular at some point, not really regular, but which has some information on the velocity, which remain L infinity on the density. So in fact, what is important to have in mind is that he introduced two energy type functions, so A1 and A2. In the first one, if you look at it, this is multiplied all the time by a weight, sigma, and this sigma is the minimum of 1 on t. That means that if t is 0, it's 0. So that means that you kill the quantity at time t equals 0. You do not ask for such kind of regularity or control at time t equal to 0. And you see here you have sigma 1 plus d everywhere. And the first constraint here, the A1, which is here, is obtained multiplying the momentum equation with sigma u dot. U dot is the total time derivative. So what is interesting is to have in mind that Hopf used the total time derivative to differentiate the equation or to get the estimate on the time derivative. This is not the time derivative, this is the total time derivative all the time. So if you multiply the momentum equation with the sigma u dot, usually when I look at regularity, I don't put the sigma and I multiply by the partial derivative in time of u and I integrate. Here I replace the guy by a weight which depend on time and which is with the total time derivative. And for the second one, you apply the total time derivative, in fact, the adjoint of the advective derivative. And if you apply it, and after you multiply by sigma 1 plus d u dot, you get such kind of terms, which is a kind of when you want to look at the regularity, you do exactly that. That means that you take the time derivative, and after you multiply by the time derivative. But here, you put inside the nonlinearity and you play with the nonlinearity all the time in order to separate terms, positive term on remaining term. So for this quantity, of course, if I calculate this quantity and I take the time derivative of this quantity and the time derivative of this quantity, I get some extra term. On this extra term, I will come back later on. Okay. So the problem is to show that A1 and A2 can be controlled globally in time. So under some assumption, the first is that if the initial data are suitable small energy, that means if you are, as I want to say that you will be close to equilibrium. If rho 0 is close to a constant infinity, and what is interesting is that in order to do so, there is something behind. It's the fact that you have some smoothing properties due to the diffusion. But let me comment about what are the objects which have the regularity. So in fact, the curl of the velocity and this guy are in fact in H1. So that means that U is not really regular. It could be Eulerian continuous in time and space, but far from zero. But in fact, this guy is regular, and this one is regular, has some control, in space control. And this guy also. And this is exactly what I said to you before. That means that you can replace divergence U by P rho up to some compact term. So that means that this is the effective flux. And these two quantities are really important in the work by Hopf. So what you can get is that you can have these continuities advected by the flow, but in such a way that F stay fairly smooth. That means this guy stay fairly smooth. So let me take care. Oh man, I don't put. Yes. Sorry. Yes. Okay. If you assume more information on the velocity, for instance, if U0 is in H1, because the one that I showed you is not for H1, is for less than H1. But if you assume for U0 in H1, which is a little bit more than what is needed by Hopf, you enlarge the control for A1 and A2. That means that you see that for A1, which is now A1 tilde, you will have a control of all these guys, but without weight in front of. You do not have sigma in front of. So that means that this will give you really a control up to a global control of this guy, and you assume it because you assume U0 in H1. Okay. And here you change just the power for sigma. It's not sigma 1 plus d, but it's sigma, but you don't care. So that means that you have better behavior close to the initial layer than the one that I showed you before. But what is interesting to have in mind is that Hopf introduced two energy functional, weighted energy functional, and it tried to relate A1 to A2 and A2 to A1 and to have a loop in order to have a global estimate. So the important remark is that in Hopf, there is an assumption which is really important, is the fact that rho 0 is L infinity. That means you start with an L infinity control for the density. So let me just explain you a little bit that of course, the propagation of the L infinity norm of the density depends on the algebraic structure of the compressible Navier-Stokes equation. Because as I said, if you look at the effective flux, when the viscosity is constant, then I explain you that this guy is compact. So that means that you can replace divergence U by this guy, which is compact, which is in H1. If it is in H1, it is in some LP. So that means that you can have a control of this guy and up to P rho. And if rho is in infinity, P rho will be controlling infinity, and that's okay. But here, if you assume to have an anisotropic viscosity, the viscosity flux is something which is regular because you have one derivative on two integrations, the Laplacian minus one here. But here you see that you have gradient, divergence, Laplacian minus one. That means the anisotropy is not so good. And the anisotropy here which since U is no more than H1, this one has no compactness. So that means that you have no up to propagate an infinity bond in this work. So it explains why it explains that up solution in all the papers which develop up solutions for compressible Navier-Stokes equation, you have the assumption that rho zero is in L infinity. But if you have an anisotropy, as I said to you, that means if you have these terms which give you a quantity which is not zero, that means some anisotropy, then it seems not possible to show that if rho zero is L infinity, rho will remain L infinity. So the work that we have developed with Cosmin Burtea, which is just some small revision for Indiana University Journal, is to say, is it possible to develop up solution in an LP framework? That means assuming only the initial density to be in some LP, and U0 in H1, don't care about to have the weakest assumption on U0, but is it possible to have some kind of up solution for this system for anisotropic viscosity? So what I want is I want to be able to treat viscous strain tensor depending on time and space. I will have a gamma which will be bigger than, so it's not equal, it's strictly bigger than d over 4 minus d. So if d equal to 2, it gives you gamma bigger than 1, which is good. And what I want to have some assumption of the viscosity. So the first assumption is that the tensor, the anisotropic tensor, you have some symmetry. So this is the usual assumption that you ask if you have anisotropic viscosity even for elliptic system. And after you have a kind of control of the coercivity. So this is just because, as I said, the viscosity, the general viscosity will be a difference on an anisotropic and an isotropic viscosity on the general first order tensor. So for this first order tensor, I assume to have a control of the first derivative in time and space, and I assume the size to be so the difference between the anisotropy and the isotropy to be controlled by this one. And this one, you see, this is almost the same one than the one that we obtained with Pierre-Emmanuel Jabin for global weak solution. So just some notation to explain you how it works, so what kind of result we obtain with Cosmin Burtea. I need only three notations. So the first one is that if you look at the energy is, so the energy, when you compare the density with the total mass and the velocity, is given by this. So this is the usual one. You have the kinetic energy, and here you have the energy coming from the pressure, which is calculated as follows. So the first one is just the relative part. If you look at this guy linked to the pressure. So these two guys, H1 here, are really well known. So this is really the energy. Okay, just talk about the energy. And there is another one which is more important, which is this one with L here, in front, with L which is 2 or 3, where you see that it gives you a sort of quantity. When L equal to 2, it's almost, so if L equal to 2, it's almost the L2 norm divided by S2. Here it's a quadratic here. And here if L is equal to 3, then you will be a kind of power 3 for the pressure. Okay, so just take into account the fact that when you will see HL, it depends on the integrability of the pressure. Okay. So let me give you a little bit the result. It's a little bit long, but I want just to explain you a little. So if you take an anisotropic viscosity, which is almost the identity plus, so you do not have a tilde, sorry, you have to delete the tilde here, is A, is the anisotropic part. So A is a first order tensor satisfying H1, H4, which is the hypothesis that I put here. So symmetry, coercivity, control of regularity, and smallness. Then there exists a global, rho u, not constant. There exists a constant, no, so there exists a constant C0 such that if the initial data have an energy small enough, so that means U0 is close to 0 and rho 0 is close to M, then you have global of solution, which are with all this control. And you see in this control, so the first is the energy, just putting multiplication and you looking at the energy. The second one is almost the A1 quantity introduced by Hopf. This one, the third one is the A2 quantity introduced by Hopf. And the third one, which is the most important one, the first one, which is the one with Cosmin-Bertheat, is the one which says something really interesting, is the fact that you see H2 here. H2 means pressure, control of the pressure in L2. So that means this is why you have here, you ask the pressure to be controlled. Pressure is rho gamma. So the pressure, the power 2 is integrable. So it's exactly what I said. But here I have a sigma. So since I have a sigma, I do not have to assume the L3 control on the pressure. I just have to write it just the L2 control of the pressure. And after I have for free a control of the pressure in L3. Okay, at the end. So that means that I have more control. So let me explain you why you see L3 and L4 in the calculation that we have done with Cosmin-Bertheat. So in Hopf calculation, as I said, everything is based on the control of the two energy functionally developed. And if you do the calculation, what you find that the control of A1 and A2 is obtained if you are able to control the velocity, the gradient of the velocity in L3 in time and space, or in L4 in time and space, but here you have a sigma in front of. The second one, you put a sigma because the A2, you have a sigma in front. But what you know, everybody, is the fact that you have the classical Calderon-Sigmund theory, which ensures you that you control gradient U if you control the curl of U, so this is for free, and the divergence of U. But as I said to you, divergence of U is not really the one that you control for compressible Navier-Stokes equation. What you control for compressible Navier-Stokes equation is the effective flux, is divergence U plus some terms in terms of the pressure. So that means that I can subtract the term with the pressure and add it. And you see that this is why I need control of the pressure in L3, because if I have control of the pressure in L3, I can have control of divergence U minus the pressure on the pressure. So that means I will have exactly the gradient U control that I need. So this is why you see the term saying that trying to have more information on the pressure will help you to conclude. So just to finish, to fix things. So in the theorem, what is really important is to have the control in terms of, you see the L4 here have the sigma in front, the power 3 are no sigma in front. This is what I said here. The power 3 has no sigma in front. Here I have to put a sigma, I forget to put it. But for 4, you need a sigma in front. So it's really good. So now to prove the construction of solution, of course, you need the easiest thing, which is pass to the limit in an approximate solution. I don't care. You write the usual one and you put the bad term in the right hand side and you regularize it. And you just need to pass to the limit after, but I don't care it. I don't want to care. I just want to write important things which help to conclude to pass to the limit and to have the stability. First is to say that the second up functional that we get without assuming rho zero in L infinity help us to have compactness on the velocity because it gives you a time derivative control of the velocity. We have also something which is really interesting is the fact that the pressure is in L2, which was not the case for weak solution à la Leray. Here, because for a weak solution à la Leray, you have something like that, so the pressure is not in L2. But here the pressure is in L2, and this is exactly the main important things, is the fact that you have the compactness of the velocity in L2, at least far from t equal to 0. You have the control of the pressure in L2. So this will help you to characterize the defect measure. That means to be able to show the compactness on the density. You just have to write just the defect measure for the pressure, defect measure for the energy. You know that you have some positivity for the two. You can get an equation on it if you play with and you look at it. You can regularize this guy because I want to show that theta is 0 if theta 0 is 0. So I regularize it as usually. I have some commutator. I multiply by this guy in order to be far from 0. So you see, this one is regular. So I multiply it and I get, and I use that gamma is strictly bigger than 1. This is really important. And you get an equation on theta, and you can let h goes to 0. If h goes to 0, this one disappears. So it remains you that if this one is 0, this one is 0, it gives you the compactness. So this is what we have done with Cosmin-Burtea. So let me explain you some comments, just give you some comments to finish. So for global weak solution à la Leray, if you want to look at anisotropy on the viscosity, there is one paper that has been written with Pierre-Emmanuel, which gives global weak solutions for the compressible Navier-Stokes equation if you have anisotropic viscosity, but with assumption of the size of the anisotropy, you have no result if the viscosity, the anisotropy is arbitrarily large. There is only one that we have written with Cosmin-Burtea in 2020 and HP, but it works because this is the stationary compressible Navier-Stokes equation. That means that you have no time derivative, so no possible oscillation in time in front of. Or semi-stationary Stokes means that you have no nonlinearity in the momentum equation except the pressure. So it is really more simple than what we have done with Pierre-Emmanuel on compressible Navier-Stokes equation. And what you have seen for the paper that we have written with Pierre-Emmanuel, we have an assumption on gamma. Gamma has to be bigger than a function depending on the dimension of the space. We have an assumption of the size of the anisotropy. And we have also the fact that the anisotropy depends only on time and not on x, but this is for simplicity, and we never wanted to develop too much complicated things on. So, but for non-stationary compressible Navier-Stokes equation with up-steep solution, that means compared to what we have done, we have a similar constraint on the anisotropic size of the viscous tensor, but we have better range on gamma because we have gamma, for instance, bigger than 1 in 2D. We can put possible space dependency of the anisotropy without too much complicated things to do. But the price that we have to pay is really strong. That means we assume more information on the initial velocity. That means, for example, H1 bond on U0. on the fact that the pressure is initially square integrable. And we also assume that the initial data is close to equilibrium instead of large data. So for conclusion, for young people who want to look at compressible Navier-Stokes equation with weak regularity, there is a really real work needed to cover more general diffusion. That means assuming anisotropy large, really large. And this is really an important problem. And I hope that you have seen the fact that you have really non-local behavior in terms of flow, which make a large problem on compressible Navier-Stokes equation. So more general anisotropic viscous tensor for non-stationary compressible Navier-Stokes equation is really an important open problem. So I will stop now. And, thank you very much.
So, other questions? So there was a clap from me, but it was silent. Sorry. I'll do it again later. Okay, so yeah, as I said, are there questions or remarks? Okay, so if this...
I have a very quick question. When you say more general anisotropy, what exactly for the viscous tensor? I mean.
Yeah, so you're right. I can explain more. It's so let me write it and try to this is. So I try to just to find the one with Pierre-Emmanuel. This is better. Okay. So you see that for instance, in the paper with Pierre-Emmanuel, if you want to consider anisotropic viscosity, what we have done, so we have the viscosity here, viscous tensor, viscosity, and you have the matrix here, the tensor, which encodes the anisotropy. And in the paper with Pierre-Emmanuel, you have an isotropic part and an anisotropic one. And for this anisotropic one, we have a constraint, which is this one. And this is the same with the Hopf solution, with the Cosmin-Burtea. We arrive at the same constraint. That means that the anisotropy here has to be controlled by the viscosity that you put, which is the isotropic part.
So this makes the tensor strongly convex, right? This constraint. So preserve ellipticity, right?
No, this is not really linked to. Yes, this is for some control. Yes, but what you see is that here you need to assume if lambda is large, then you can have an isotropy which is large. But if you for instance want to assume just to have this one, okay, let me put so I try to find one which is more simple. Just this is it. Okay, if you want just to take this one for instance, but now with mu x and mu z, for instance mu z which will be epsilon, which is small, and mu x which is order 1. And this is exactly the one that you have, for instance, for geophysical flows, where the viscosity is small in the vertical direction and large in the horizontal one. Then nothing has been done.
Okay.
So this is why there is some, except if you play with the lambda, that means with the bulk viscosity. If the bulk viscosity is large, then the difference of these two guys may be large, because you have in the constraint we obtain with Pierre-Emmanuel the lambda in the right hand side. So when I said more general, I said without such kind of constraint compared to the isotropic viscosity. And this is really linked to the because if you put large anisotropy, that means that you put large non-local behavior inside the transport equation. And this is why this is so interesting to work in. That means you are in a not regular framework, you are in between. We want to allow the density to remain, for instance, only an infinity or only L gamma for the weak solution. But you want to put some non-local behavior inside.
Yeah. Thank you. Very nice talk.
Thank you, Anna.
Okay. So let me see, are there other questions? If not, we can proceed with the next talk. And thanks, Didier, again.
Thank you.
How you can hear it? Good. Okay, and so I guess that, let me see. So the next speaker is Jacob Bedrosian. Good. So we can see.
Okay, great. Yeah, I'm going to try actually using two devices. I normally don't, but we'll see if it works.
Let's see. Okay, so the next speaker is Jacob Bedrosian from Maryland, University of Maryland, and he will talk about positively Aponev exponents for the 2D Galerkin Navier-Stokes with stochastic forcing.
Okay, great. Yeah, thanks for the invitation. It's too bad we can't be there in person. I, for one, very much miss more in-person conferences, though a few have started. So maybe we'll next time. Okay, so everything I'm going to talk about is joint with Alex Blumenthal and Sam Punchin-Smith, who used to be at Maryland but are now elsewhere. So Alex is at Georgia Tech and Sam is at the IAS right now. Okay, so I'm going to be talking about the Navier-Stokes equations. I guess this conference I don't need to review them. The talk will actually not directly discuss the Navier-Stokes too frequently, but just to remind, I'm going to be actually dealing with the 2D case for this talk in vorticity form. So in this case, you just get scalar transport for the 2D case. Right, so when nu goes to 0, then the viscosity goes 0, you often see turbulence. You can see a bunch of other things, but you often at least see a lot of turbulence. Looks very different in 2D and 3D, but you still see some variations thereof. I don't want to overcharacterize it, but essentially some things that you see are in particular chaos. That's an important property that is often overlooked. And you see anomalous dissipation in the spread of energy over a wide range of scales, or energy and entropy or other conserved quantities over wide ranges of scales. I will not really be talking about turbulence today. What I will be talking about is trying to prove chaos for at least the finite dimensional approximations, and with at least stochastic forcing. So finite dimensional approximations, they aren't turbulent in any sense. No matter, if you fix the dimension and send nu to 0, you will not see turbulence, and that's because turbulence is inherently an infinite dimensional thing. So in 3D Navier-Stokes, for example, you see the creation of all these small scales over here, and you can see this is a log-log plot of the power spectrum. So here is the expected value of the energy frequency k, and you can see the spreading of energy to more and more frequencies. And so obviously, if you fix the dimension and try to send nu to 0, you're not going to see this picture. You cannot see this picture. You'll see some weird something else. Okay. And so the talk will actually not be on turbulence, but of course the goal is to find mathematical techniques that can build us ever and ever closer to understanding turbulence in the actual Navier-Stokes equations. Like I said, in 2D and 3D, the dynamics are rather different, but they're both turbulent in some sense. So in 2D, it's actually more complicated because you actually have cascades in both directions, but I won't discuss. I think Francisca talked about this yesterday. Okay, so just as a quick aside, so why am I using random forcing? There's a couple of reasons why I think it's a reasonable way to attack this problem long term. So first of all, most settings, the sort of simplest setting that you study in the physics literature is actually kind of a statistical stationary in time setting. So here you put in some external forcing, you send time to infinity, and then you send nu to 0. Of course, you don't settle into an actual steady state, you settle into a statistical steady state. And so dealing with probability and random forcing is a natural setting for dealing with statistical steady states. While of course you don't need randomness to deal with statistical steady states if you have some kind of invariant measure. But reasonable invariant measures, we actually only know how to construct, even for most finite dimensional systems, if there's random forcing. Doesn't necessarily have to be one in time random forcing, but you need some kind of random forcing generally to do something like this. And so at least if you study random or stochastic forcing, you at least have objects to study. you at least qualitatively have the existence of objects that you want to study when you send nu to 0, when you send runners up to infinity. And from a practical perspective, they don't really observe much difference in the statistics between random and between deterministic and stochastic forcing. It's not really expected to make a difference in most of the basic statistical questions you might want to ask. Mathematically, there's a big gain because random dynamical systems has a lot more robust tools than deterministic dynamics. And here I'm going to be discussing specifically to prove chaos. So by chaos here, I mean a positive Lyapunov exponent. So here, so let's say I have a finite dimensional dynamical system and I have some evolution. So this is a map that takes the initial condition to the future configuration. So in the case of the Navier-Stokes equations, just gives the vorticity, maps it to the future vorticity. And what I want to understand is if I take the derivative of this flow map with respect to the initial condition, does this grow exponentially or not? And this basically tells you that so if lambda 1's positive, then small changes in the initial condition explode exponentially fast. And for example, for a finite dimensional differential equation with Lipschitz coefficients, this is as fast as you could possibly separate solutions. So this is kind of normally in the kind of popular literature called the butterfly effect. So I'm going to call this chaotic if lambda 1 is positive, kind of almost everywhere. At least for random systems, it's reasonable to ask that it's positive everywhere or almost everywhere. Now in finite dimensions, even in finite dimensions, if you have deterministic forcing, it's almost impossible to verify this for even relatively easy systems. So only extremely rigid systems like axiom A flows or NSO flows, things like this are only known. And these systems are not really don't really match physically interesting systems very closely, with some exceptions, of course. But basically, it's extremely hard to verify chaos for any deterministic system, with some exceptions. You see chaos in a lot of systems that we can't verify for mathematical. So we're going to do it with stochastic systems. So we're going to use stochastic forcing, for which you have more tools, and we're going to do it for finite dimensional approximations to the Navier-Stokes equations. So this is the sort of final theorem we're going towards. So take the 2D Navier-Stokes equations with on a periodic box, project to finitely many frequencies. So, the Fourier transform lives on a lattice. All I'm going to say is take only the modes in some big box on the lattice. So that's what this notation means. Just the complex numbers just indexed over a truncated two-dimensional lattice. These are my unknowns. And if you work out what the nonlinear term looks like, it's this with some coefficients. And you have, this is the viscosity right here. And then I'm going to have some stochastic forcing. So don't need to worry too much about the exact form of stochastic forcing. Suffice it to say it is additive. So alpha and beta are just constants. They don't depend on the vorticity. And they don't all need to be non-zero. Just a couple of them need to be non-zero. And that suffices, regardless of what n is. That is stuff that was worked out a long time ago. So the theorem says if you have a high enough dimensional system, so you include enough frequencies, and you sort of force a couple of modes, then there always exists a Lyapunov exponent, which is independent of the initial condition or the random noise path, which is strictly positive. You have this very bad quantitative estimate, but it is a quantitative estimate at least. And this is definitely coming from the nonlinearity, because if you didn't have the nonlinearity, you can prove that lambda 1 is negative for all epsilon. It's negative all the time. And you can also prove that if epsilon is large rather than small, so if you're looking at the low Reynolds number case, then also you can prove that lambda 1 is negative. So it's something that is only true when epsilon is sufficiently small for you to see this chaos. Okay. And it's somehow non-perturbative, because you're really sending, this is really a theorem about for all epsilon sufficiently small. So you're not looking at some kind of borderline regime where you just transition from stability to instability. So it's not perturbative in this sense, that this kind of result. Okay, so how do we prove this theorem? So I'll discuss a little bit of it. So it's proved over 2 papers, essentially. In the first paper with Sam, and Alex, we proved a sufficient condition for a general class of systems that look like Navier-Stokes. And then in a follow-up paper with Sam, we verified this condition specifically for Navier-Stokes. Okay, so suppose I have just a general system, just for the sake of argument. Let's say that it's posed on Rn, which is essentially like the system we have here. So these xj's are vector fields. And I want to deal with SDEs, which are globally well posed in time, like the stochastic Navier-Stokes equations, if you truncate to finite dimensions. And so once that's true, then they define a stochastic flow of diffeomorphisms. So this is just the random analog of this flow map that takes the initial condition to the future state of the system. So, but it depends on both the initial condition and on the random noise path. Now you can associate with these, with the solution of the SDE, Markov semigroups. So you have a Markov kernel, which tells you, if you know the initial condition, what is the probability of finding the solution in some set at a future time. And so this gives you two semigroups, one that tells you how observables evolve. So that's just the expectation of some observable given that you know the initial condition. And then the other thing is, if you know that the initial condition, let's use W, is distributed like mu in law, then PT star mu is the law of the solution at a future time. So this is the dual Markov semigroup. It's like the, yeah. Both of these, because I'm dealing with finite dimensions, both of these actually solve PDEs. So in particular, they solve these PDEs. So L is, just by terminology, what is called the generator, but in some sense, in some moral sense, L and L star are kind of on equal footing of importance. Notice that, if your system was deterministic, these would just be first order transport equations, but if the randomness produces second order terms. Now, these aren't necessarily elliptic unless you force every mode, but because basically you need these vector fields to span Rn in order for the system to be elliptic. And yes, I'm using vector fields and directional derivatives interchangeably. It's very convenient once you get over the notation issue. Okay, so the main object, one of the main objects of study when studying stochastic problems is the stationary measures. So these are the measures for which the law doesn't change. So if you've never worked with random systems before, the example I always give is kind of like flow over a stone in a river. If you stare at that for a little while, you realize you're looking at the stationary measure of a Markov process, whether it's not exactly a Markov process in real life, but think of it like that. So it's like a statistical stationary solution that you're looking at. The statistics aren't changing in time, but the solution is. I'm going to be working in a case where we have a unique stationary measure. This is not hard to verify. Well, it is well known how to verify this for the Galerkin and Navier-Stokes under the conditions that I've imposed. Basically, you need two components. You need that it's sufficient to prove that the Markov semigroup is regularizing in some way. And you need to prove some sort of irreducibility, which says that no part of phase space is disconnected from another part of phase space. So you have a kind of positive probability of a trajectory going somewhere else, going anywhere else. So that's called irreducibility. There are many variations of this, but it's sufficient to go with these two properties. The regularization is not as strong as requiring ellipticity because these Markov semigroups can be smoothing without being elliptic, or without being strictly parabolic, so to speak. This effect is called hypoellipticity, and it will be important for my talk, not just for fun. You'll see it's of fundamental importance to what I'm talking about. Okay, now once you have this nice qualitative theory, actually, there's a beautiful theorem from dynamical systems, or from random dynamical systems, both in a sense, called the multiplicative ergodic theorem, which tells you that under some very basic assumptions, which are not hard to verify for Navier-Stokes, that there actually exists Lyapunov exponents. And not only that, but they are deterministic and independent of the initial condition. So you have these, and you actually have an entire spectrum, but I'm only going to talk about two: the top one, and the total, or the sum, the total Lyapunov exponent. So this tells you the asymptotic exponential growth rate of the gradient of the flow map, and this tells you the asymptotic exponential growth rate of the compression or expansion of Lebesgue measure. And they are related by this. N is the dimension of the space. So it has to do with how many frequencies you took in your Galerkin truncation. So if you think about this ergodic theorem, it's a really beautiful theorem. It gives you, for kind of ergodic systems, what spectral theory gave you for stationary systems. So because let's say we have additive forcing, which is actually the case I'm interested in. You think about this matrix, this Jacobian matrix. What the multiplicative ergodic theorem is giving you is some kind of spectral decomposition asymptotically of J as time goes to infinity. It's going to give you a spectrum of exponential growth rates of J, even though this is a time-dependent linear system. So if WT were stationary, this would be like an eigenvalue decomposition of a fixed matrix. But the multiplicative ergodic theorem can do it if WT, instead of being stationary, is kind of statistically stationary as time goes to infinity. So the multiplicative ergodic theorem is really a powerful tool here. But it's all very well understood. So the existence of Lyapunov exponents is not a new result. It's just is. It's in fact, it's not even often not that hard to verify even in infinite dimensional systems that there exists. But the hard part is how do you estimate them? And this is actually very hard because of cancellations, problems with cancellations. So let me just show you a Tor example for why generally it's really hard to get anything quantitative about Lyapunov exponents. And let's just show suppose I'm just taking IID determinant 1 matrices and just multiplying them together. And I want to ask, when does this random matrix multiplication grow exponentially? This is actually a pretty good toy model if you think about the chain rule, a pretty good toy model for asking whether or not the gradient of a flow map will grow exponentially. But this is simpler, obviously. So we can come up with some examples where obviously it doesn't grow. So if AJ is almost surely a random rotation, obviously there's no growth. If the AJs are always a shear, some kind of shearing, then there'll be growth, but it won't be exponential. So the exponent will be 0. The third example is the more complicated one, where suppose that, and the way you should really think of it is suppose that P is equal to 0.99999 or whatever. So that almost all the time, you're going to double the x-axis and have the y-axis with this matrix action. So you're going to stretch the x-axis out exponentially fast for a really long time and compress the y-axis. But then every so often, those two flip. And then it's going to be the same thing over again, where you're going to, all that expansion that you built up in the x direction is now going to get compressed. And then it's going to flip, and then it's going to get expanded again. And it's going to flip, and it's going to get compressed again. And so basically, these will cancel out over long periods of time. If you watch long enough, you realize that actually you will not see exponential growth here. And of course, this is maybe not so hard to figure out if you're talking about random matrices. But if you think about a dynamical system that's evolving all over phase space in a pretty complicated way, it's really hard to keep track of this. So even very simple and basically explicit systems, it's extremely hard to know whether or not you can have a positive Lyapunov exponent on a positive measure set. And so the point is that randomness will make this a lot easier. And the hint for this came from Furstenberg in 1968, who proved this amazing theorem, which says that for random matrices, for determinant 1 random matrices in, let's say, 2 by 2 random matrices, these 3 examples are basically the only cases where lambda is equal to 0, more or less, up to a deterministic change of basis. And that's a very deep theorem that uses a couple of interesting properties of matrices and of Lyapunov exponents. But that's a hint that randomness should make this a lot easier. Okay, so this previous discussion hints that a lot of things about Lyapunov exponents really about tracking directions. You want to keep track of which directions are expanding and which directions are compressing. And so that motivated Furstenberg to introduce this process, which I'll call the projective process, which is just the normalized gradient process. So VT is stuck on the sphere. And this Z process should be WV. And yeah, so it is not a Markov process. VT is not Markov. But in fact, if you couple it with W, then it is Markov. And in fact, you can prove that the coupled WV process solves its own SDE that lives on the sphere bundle of the configuration space. So yes, we will also have to do some PDEs on manifolds. Even if you don't like manifolds, you cannot avoid it in this talk or in this project. And right, so these lifted vector fields are now vector fields that live on this manifold, the tangent space of this manifold, and they're like this. So they're kind of ugly, but they're not that ugly. I'm going to be working under the assumption, which we're going to have to prove for the Navier-Stokes equation specifically, that this SDE now on this manifold has also a unique stationary measure. So the generators and Markov semigroups all denote the twiddles. Okay, so why do we care about this? Well, the stationary measures of the ZT process encode statistics about what directions are expanding and compressing. And if you think about this, think about if you're having some expansion somewhere. So let's think about the system. Well, okay, let's let's just think about the vector. So let's think about a vector that's kind of expanding in the x direction and compressing in the y direction. If you normalize this, this is going to converge exponentially to this. So it's you're going to, if you have expansion in the flow map, you're going to get compression along the sphere. So VT, the sort of normalized flow map, will compress. And so the compression and expansion on the sphere is now what corresponds to expansion and compression in the flow map. But it's reversed actually. So expansion in the flow map is compression on the sphere for VT. And that's a very deep and important fact. And that's what underlies actually the next theorem. So this observation from the ergodic theorem is actually not that useful, in fact, because this quantity is not sign definite. So you don't really know what this is. This is the stationary measure for the projective process. But okay, this formula is not that useful. The next formula can be extremely useful, but it's very complicated. So let me explain what it is basically heuristically. So this is a stationary measure on the sphere bundle. But you can kind of think of it as a smooth function, right? I mean, the cases that we're studying, actually, it's a smooth density. So you can think of it just, if you fix W and just look at it as a function of V. So you're going to disintegrate for each W, there's a sort of measure on V space on the sphere. And so you have some measure on the sphere, which I'll draw as a one-dimensional periodic interval. So every point in W space has its own little sphere in V. Does that make sense? And now what this formula tells you is that I can express the Lyapunov exponent by flowing the base point forward, and then looking at the relative entropy between this, and then if I pushed forward this density over here, push forward by d phi t, by the gradient of the flow map, and that's going to push forward to some other thing that doesn't have to be the same, right? They're only kind of the same if you average over all trajectories or something. But point by omega, there's no reason that there should be related at all, essentially. And if you look at the relative entropy and average over all the trajectories, this relative entropy difference gives you exactly the gap between the two exponents. So remember, n lambda 1 is always bigger than equal to lambda sigma. And it's a really deep, the proof is actually a little easier than the depth of the inequality suggests. So it's all about tracking compression and expansion on the sphere. But the reason why this is useful is that this is a sign definite quantity. And so that opens the way for getting positive, quantitative estimates, potentially. Though actually that's very hard. So one consequence that's used often, these techniques are called a la Furstenberg, is that if this is equal, that can only happen if and only if this is true almost surely. And that's a really strong amount of rigidity, because this has to hold for all omega, so all possible noise paths. And oftentimes in a lot of systems, this can be sort of relatively easily ruled out. So this is actually, there's a paper by Sam and Alex and I from a couple of years ago that studied the actual infinite dimensional Navier-Stokes in a periodic box. But instead of studying chaos of the vorticity field, chaos of particles immersed in the fluid. So whether or not the particles moving around experienced what's called Lagrangian chaos, so whether or not the Lagrangian flow map was chaotic. And we used the version of Alla Furstenberg for this setting. The reason it worked really well there is because of incompressibility, because the total Lyapunov exponent of the Lagrangian flow map was 0. And so now if you prove that n lambda 1 is strictly bigger than lambda sigma, if that's 0, then you get chaos. Right? But that's not the case if you want to study a lot of other dynamical systems where lambda sigma is negative. And so this doesn't really give you that much if lambda sigma is not, if lambda sigma is negative, and there's nothing quantitative about these arguments at all. So what we needed was a quantitative way of dealing with it, but this is a very inconvenient quantity to get quantitative estimates on, because this is really complicated. It's really hard to figure out what's going on. And so the first thing that Sam and Alex and I did was find a new expression for Lyapunov exponents that should be more easy to get quantitative estimates on. And essentially what we did was we saw a relative entropy, and having learned some statistical mechanics and kinetic theory and stuff, we just took a time derivative, because that's what you do with relative entropies. And indeed, you get Fisher information quantities. So here, F is now definitely a smooth quantity, which is the density corresponding to the stationary measure of the projection process. And let me just draw attention to this formula, because that's the only one that's really of relevance. We actually have a third formula somewhere in the paper, but yeah. And so the point is, this on this side of the equation is some kind of Fisher information. It's like almost like a gradient of the logarithm in L2. And on this side is something relating to the Lyapunov exponent gap. In fact, there's an exact time infinitesimal analog of the previous inequality, but it's just not what we're going to use. So we're going to use the second formula, because that's going to work for us. And now it's going to be useful to give you quantitative estimates. So let me throw that small noise parameter in here. And the vector fields will also be parameterized by epsilon, as is the case for Navier-Stokes. And then the formula becomes this. If you track the epsilons, that's what happens. And so the left-hand side is positive definite, and it's directly on the stationary measure, which is great. But it only contains derivatives only in the forcing directions. And they're lifted derivatives, and they definitely will not span the tangent space of this sphere bundle manifold thing, right? It's not going to span this tangent space of Rn cross Sn, or Rn cross Sn minus 1. And so this doesn't tell you that the Lyapunov exponent gap is somehow bounded below by HS or something. But that's exactly what we're going to prove on the next slide. I'm going to state the theorem, actually 2 slides, and state the theorem, but I'm not going to prove it on this slide because it's a long proof. But so basically, what we want to do is we want to relate these derivatives to all of the other derivatives on the entire manifold, right? So hypoellipticity is exactly the right concept for this. So this is the concept that, Kolmogorov actually first observed it in a simple example, and Hermander found the kind of basically sharp condition for this. So this is the question of if I have a Markov semigroup. So I have a system like x0. I've got a generator like this. When is this, or the elliptic question, when is this regularizing? Even if it's not elliptic. And actually, here's the condition. So suppose I have a collection of vector fields on a manifold. Now the first collection I'm going to denote is just going to be the forcing directions. Then I'm going to successively create more directions, potentially, by commuting the directions I had previously and the directions that I have. So that kind of was vague. I had a set of vector fields Z0 through ZR. And I want to create new ones by commuting guys from the previous step with the original R vector field, or R+1 vector fields. Okay. So ellipticity is just requiring that this thing spans the tangent space. Hyperellipticity is requiring that eventually these new Lie algebra thingies are going to span the tangent space. So a priori, in general, a much weaker condition. And this is called the parabolic Hermander condition. So it is sufficient to imply that the parabolic semigroup associated with this Markov's, the parabolic semigroup associated with this generator is regularizing. So it instantly maps L infinity things to C infinity. And so in particular, if the lifted vector fields are hypoelliptic, then that's good. Then P twiddle T is, sorry, if the lifted vector fields satisfy this Hermite condition, then the semigroup is hypoelliptic. So I'm going to call this projective PHC, so projective parabolic Hermite condition. So the parabolic Hermite condition for the Navier-Stokes equations has already been verified by Wiedemann and Jonathan Mattingly in 2001. So that's well understood. But to do it for the projectivization, this lifted thing is much harder. But suppose that I knew that, then the next sort of, this is kind of like the quantitative or technical meat of the general method for estimating Lyapunov exponents, which is I have a generator which depends on epsilon, and so I have a stationary measure which depends on epsilon. And I have a Fisher information which depends on epsilon in some way. I have no idea, right? But then how do I put this information together to get something? So the following is actually a PDE estimate, and just tells you that assuming that my dynamical system vector fields are sort of uniformly controlled in epsilon and they satisfy this projective parabolic Hermite, then I get this uniform in epsilon lower bound or upper bound. And in particular, neither S star nor C depends on epsilon. So this depends on epsilon, but none of the constants depend on epsilon. So it's a uniform a priori regularity estimate on this P. That's what's going on here. And it's a long story how to prove this. But once you have this, then you get this lower bound on the Lyapunov exponent gap. So capital C doesn't depend on epsilon, S star doesn't depend on epsilon. The only thing that really depends on epsilon is here and here. And of course, these guys depend on epsilon. Right, so the proof of this uses techniques that go back to Hermander. It's kind of like an L1 variation of hypoelliptic regularity theory on a manifold. It has to be on a manifold. But anyway, there's some tricks due to Hermander, but the Hermander worked in L2, which is self-dual, and certain aspects are a lot easier if you're self-dual. And so if you're L1, if you're trying to do like an L1 theory of hyperellipticity, it can be trickier. And for some reason, I couldn't find it in the literature. Though if you're not trying to get specifically certain types of quantitative estimates, I can't think of a reason why someone would go to the trouble. So kind of the fact that the necessary inequalities didn't exist kind of probably came from the fact that no one tried to prove an inequality using the Fisher information in this way. Though I'm not going to say it definitely doesn't exist somewhere, but some version of this doesn't exist. Okay, so now I'm interested in, now I want to come back to the Navier-Stokes equations, or in fact, just a general class of equations which look like the Navier-Stokes equation, go like truncations. So I have a quadratic nonlinearity, which is bilinear. I have a Navier, I have some kind of damping. So A is an arbitrary symmetric positive definite matrix. And I have these guys are constant vector fields. So again, I don't want to deal with multiplicative forcing. And I have this scaling. So this balance between epsilon and square root of epsilon is such that the energy remains uniformly bounded as epsilon goes down to 0. It remains uniformly bounded above and sort of uniformly bounded below. So actually, if you look at the stationary measures, so for every epsilon, there's a stationary measure for this process. You can actually prove uniform upper and lower bounds on the density of the stationary measure using just hypoellipticity. And it's some uniform hypoelliptic regularity estimates. This is done by a student and I recently. But I won't talk too much about that. And of course, I should mention these two properties are what we need for this method to work. So these are the two properties that make it Navier-Stokes-like, or the nonlinearity makes it Euler-like. Conserves energy or entropy, depending on if you're talking about 2D or 3D, and it preserves phase space volume. This is the fact that it's Hamiltonian, or some kind of degenerate Hamiltonian. It's also this particular condition, but let's just say xk you're forcing on eigenfunctions of the Stokes operator, whatever. Okay, so then basically in our first paper, Sam and Alex and I proved that if you can verify projective parabolic harmonic condition, then you have chaos for all of these systems on the previous slide. So for all systems of this form, projective parabolic harmonic is sufficient to imply chaos for epsilon small, and you get this kind of almost surely suboptimal bound. So in our first paper, we actually used this to prove chaos for Lorentz 96, which is a fairly well-known toy model used in the applied literature to test numerical methods and other ideas for high-dimensional chaotic systems, but it's much simpler than Navier-Stokes. So we can kind of verify projective parabolic harmonic kind of by hand, in a sense. So previous quantitative estimates on Lyapunov exponents do exist in literature, and what those other existing works that I'm aware of are doing is they take a much simpler system and getting a much more precise estimate on lambda 1. So they can take simpler systems like 2D nonlinear oscillators and actually get an asymptotic expansion for the Lyapunov exponent as epsilon goes to 0. So that's pretty interesting work, but you really need almost exact understanding of the projective stationary measures, which we're not going to get for Navier-Stokes, not now, probably not ever. So the purpose of the method that we designed was specifically to be robust to a lack of information. So we're not going to understand the Navier-Stokes equations anytime soon, not completely, I mean, and so we shouldn't kind of depend on methods that require that. Okay, so let me discuss this conditional theorem for a second, and then I'll go back and discuss how you actually verify it for Navier-Stokes. So basically, there's some nice exercises in some PDE theory and stochastic ODEs to verify all the qualitative properties that I claimed. So if you have projective hyperellipticity, you have to verify the existence of uniqueness and regularity of all these measures. But okay, it's a fun exercise, but it's just an exercise. Now, one thing is that the Hamiltonianness of the energy, of the nonlinearity, anyway, volume preserving of the nonlinearity implies that we actually know what the total Lyapunov exponent is. It's just from the dissipation. So it's minus epsilon times a trace of A. And so the Fisher information lower bound, all that machinery that we built, gives us this lower bound. So in particular, this guy is going to be an order 1 term. And so this guy is the guy we're trying to bound from below. And so what we're going to say is, well, suppose that it was bounded. Then I would get a uniform regularity estimate on the stationary measure in some positive regularity sublevel of space. So S star is some number between 0 and 1. Think of it as very close to 0. It depends on the dimension. It's like 1 over dimension kind of. So as epsilon goes down to 0, so as the Reynolds number, so to speak, goes to infinity, the stationary measure actually converges strongly in L1 to an absolute continuous density for the deterministic Euler equations. Again, in particular, the projective Euler equations. And here's where you can't escape knowing some deterministic dynamical systems, because you need to use facts from deterministic dynamical systems here in the limit. Because you need to prove that somehow this is bad. That somehow you need to prove that can't happen. So what's the intuition? So the idea is that, remember how I said growth of the gradient of the flow map implies compression in projective space, or compression on the sphere. So the point is that if you have a random system, then every time you go back to a configuration or anything like that, you can generally going to be pointed in some kind of different direction, and these compressions will average out. And so you can have a positive Lyapunov exponent and still have a smooth stationary measure. But if you have a deterministic invariant measure, that is no longer true. So you cannot have an L1 invariant measure for a deterministic system on the sphere bundle if you have any unbounded growth in the gradient. Unbounded growth on a positive measure set, because on those trajectories, you'll need to compress the sphere into a delta function in the direction of expansion, basically. So that's a rigidity theorem from deterministic dynamical systems. And so now you have to prove some growth at the level of this deterministic dynamical system. And that's where basically the special scale invariance of the nonlinear Euler equations basically rescues you. So the fact that you're dealing with a quadratic nonlinearity, or in particular a polynomial, a homogeneous polynomial nonlinearity, gives you some scaling invariance And that tells you that you're always going to have some gradients of the flow map growing. And so this general argument will work for lots of systems if you verify these several things. But actually verifying these things is actually not that easy. If I have time at the end, I'll discuss a little bit. But we also hope that more precise quantitative estimates will come later with more precise understanding bit by bit. Okay, so now for Navier-Stokes, remember this is our nice ugly SDE. You want to prove that if you take this nonlinearity and lift it to the sphere bundle, that somehow this thing satisfies Hermander's condition. So that's pretty not obvious to verify projective hyperelliptic. To verify Hermander's condition. This is what Sam and I did in our follow-up paper. So there's a couple of steps. So the first step is actually has to do with thinking this certain special geometrical structure to this lifting procedure. In particular, it's a Lie algebra isomorphism. And that's really important. And the fact that our geometry, our underlying configuration space is flat means that basically the question will be the same everywhere. So that's also important. And fiddling around with the complex structure of the underlying unknown and fiddling around with these special geometric properties of lifting vector fields onto sphere bundles, you can prove this lemma, which reduces the question to something which is purely algebraic. So you have some collection of matrices, which are basically the second derivative of the nonlinearity in a certain component. But if you look at that for a second, you realize that's what it is. But this is the nonlinearity, and this is our matrix. All right. So you have a collection of traceless matrices, basically just derivatives of the nonlinearity. And actually, what we can prove is that it's sufficient, sort of almost necessary, but not actually necessary, sufficient to prove that if you take linear combinations and commutators of these real value matrices, you can generate all trace-free matrices. So this notation, this weird notation, just means that these matrices are indexed by points in the truncated two-dimensional lattice. So it's purely algebraic and depends only on the nonlinearity. So there's no noise anymore, and it's just an algebraic question. So you can force every mode if you want, and it won't make the question easier. Okay, so this is just a property of the nonlinearity. But at least you only have one Lie algebra to verify. It's actually it's just a purely algebraic problem. But the problem is these matrices are still too complicated. I have no idea how to verify this by hand. I mean, for Lorentz 96, you can do it because these matrices are like 4x4 or 2x2 or something, and very easily manageable. For these guys, all the modes are coupled to all the other modes, and it's just a completely crazy mess. And so basically, we had to go read about matrix Lie algebras and find some methods that could do this. And the observation that's crucial is the following: if you have a diagonal matrix in your Lie algebra, and you commute it with an elementary matrix, you're going to get this identity. So this is a matrix which is 1 in the ith entry, but one in the ijth entry and 0 in all the other entries. So does that make sense? Yeah. And actually, so it turns out that this is actually a eigenvector-eigenvalue pair if you think about linear operators on matrices. And so if you can find some diagonal matrix such that di minus dj is not equal to di prime minus dj prime for all pairs of pairs, so to speak, then you have a linear operator with simple eigenvalues. And so when you iterate it, when you just apply it to a bunch of things, you're going to find all of the eigenvectors that are supported in whatever you're iterating on. So roughly speaking, it's called a Krylov subspace. It's actually a numerical method. It's a well-known type of numerical method for finding eigenvectors and eigenvalues of matrices. And so if you can find one D with this distinct differences property, then you can form a bunch of other directions in your Lie algebra. So I'm lying a little bit. Well, I'm not lying, but you can't find a D which satisfies that property in our Lie algebra because there are some symmetries which make this, which degenerates it. But okay, so you have to prove a lemma that says kind of like if you can find a single diagonal matrix which has as many distinctness, which is as distinct as possible, then you're done. And suppose you had this lemma, then you're just trying to find a diagonal matrix which is kind of distinct enough. So the idea is you can find some diagonal matrices, which happens to be this trick, and that is there's some deep reason for why it's k and minus k. So if you look at the commutator, that works out. So if you commute hk and h minus k, so this is like the kind of looking at the interplay between sines and cosines at a particular mode. So it's like a phase shift of each other. The goal is to put these together in a clever linear combination such that D star is kind of generic. So you want to say, okay, suppose that you want to say it's always possible to find some linear combination that's kind of generic enough. And so you say, well, it's going to be the same as saying for all possible combinations in your constraint set that satisfies some Fourier condition that there exists one example of these matrices that witnesses some kind of non-degeneracy. So this is the fact that you can choose alpha j arbitrarily, and so this is a slight thing. And then you say, well, if I need to find only one witness, then the opposite of that is that there are no witnesses. So basically, what I want to prove is that there are no solutions to the following set of algebraic equations. No solutions, and there's a constraint set, which is algebraically defined. And so if there were no Galerkin truncation, then actually these guys would actually be algebraic. This would be a list of polynomials in 8 variables and integer coefficients. And I need to prove that this thing is inconsistent. And that is okay. There are methods for that, right? In particular, we're going to use algebraic geometry methods. There's a host of computational algebraic geometry methods specifically for proving that systems are inconsistent. So it's a whole set of methods for this, and we're going to use them. There are two issues with using them. So one issue is that they are not algebraic equations because of the Galerkin truncation. So it turns out you can get around this by hacking up the frequencies in some complicated way and reducing the problem to something like 32 different polynomial systems that all need to be proved inconsistent. So it's annoying, but it's doable. The other thing that one has to observe is that if you want to prove this theorem for all n, you obviously can't just kind of do it brute force. So you need to use a more structure in the problem to reduce the system, to reduce this question to something that's going to work for arbitrary Galerkin truncations, not just a Galerkin truncation that I give you. Right? And the idea here, the important property here, and there's a little bit of algebra underlying it, easy algebra underlying it, which is that these guys are not only are they polynomials in I, J, L, and M, but they're also polynomials in K, right? And so there's kind of right? And I mean, I'm going to clear the denominator. So technically I should say the rational equations. But I'm going to clear all the denominators. I'm going to get big polynomials. And so using the fact that they're polynomials or rational also in K, I can do some magic and actually come up with a proof which is computer assisted, but in one single swoop, basically verifies it for all Galerkin truncations sufficiently high. And this 396 is basically just related to how we hack up the problem into different subproblems. So there's nothing magical about 396, and there's no way it's sharp. Yeah, so that's how we verify the condition. So okay, so I would say that wasn't that, I didn't find that easy personally, but we seems like there's still a lot of room for improvements. So for example, this is actually a big one. This was not a hard step for Navier-Stokes and Euler. You know, this was not a hard step for Euler to verify this growth, but actually for a lot of dynamical systems, this can be an extremely hard problem. It's not as hard as proving exponential growth, but you still need to prove some growth, and that's difficult. And that's just if we want to use this kind of compactness rigidity argument that we have. So even this compactness rigidity argument is pretty hard to use, and it's still a little bit, well, you want to get better quantitative estimates and get a better understanding than what the compactness rigidity argument can afford. So other directions would be, you know, better hypoelliptic tools. I'm not sure that that we have the best hypoelliptic inequality in terms of scaling and epsilon and whatnot. So you might be able to get some improvements just from there and whatnot. So obviously you can tell that the technique works in sort of arbitrarily high dimensional systems. So that's good. But extending it to infinite dimensions, there's a lot of challenges in that direction. That's very interesting, but it doesn't give a clear path forward. Not yet, anyway. Okay. Thanks, everyone.
Thank you very much for this very interesting talk. Okay, let me see. Are there questions?
Okay, I don't know, maybe it's gonna be a stupid question or no, because it was an impressive talk. So you always consider the case of additive noise, but I mean, is there any chance to generalize this to multiplicative noise? And in particular, it would be interesting understanding if there is some way for transport noise, so of the form, I don't know, sigma k scalar gradient of vorticity in DWK.
Right. Yeah, I would say there's some aspects of the method that work just fine in multiplicative noise, like the sort of the backbone of the. So this lower bound is proved for completely general SDE. In fact, even on a kind of general geodesically complete manifold, blah blah. So this kind of aspect of the method works totally fine in multiplicative noise. The thing that will be difficult is, I think, for something like Navier-Stokes. Actually, one needs to verify the projective hyperellipticity. And this, our method, is definitely designed for additive noise. I think that it should be doable. So, and then once you have projective hyperellipticity, let's see. If you can verify projective hyperellipticity and nothing bad happens to the tails of your distribution functions and stuff like that, which I don't think should be a problem, then I more or less claim that it should work. But yeah. So
if I can ask, if I understood correctly your presentation, but I'm not sure. The point is, like, with additive noise, you have this somewhat simplification, but at some point you only need to checking this only depends on the nonlinearity itself, as soon as the noise is already hyperelliptic, if I understood correctly.
Yes. Yeah. So as soon as this noise is
more true in the multiplicative case, or
not necessarily, no. And it might be, you might be able to well, I think it a little bit depends on the structure of the denominator. I mean, in some sense, having multiplicative noise should make projective hyperellipticity easier, or could, in theory, make it easier, because when you lift it, you actually have directions in the tangent space already. Whereas additive noise, when you lift it, you don't get anything new at all, right? Because the derivative of the noise is zero. And so there is a potential advantage. So for example, if you come up with, you can actually come up with really complicated multiplicative noise, which is actually, when you lift it to the sphere bundle, is actually elliptic, which is not that obvious, but you can. And you don't want to use that noise. So for transport noise, or something like transport, yeah, some combination of transport noise and added forcing or something like that, yeah, I would say it's definitely it's not a trivial consequence at all of what Sam and I did, but I also would think that it is potentially possible. Yeah, but you need this hyperplasticity condition, and that for the finite dimensional Goldkin-Navier-Stokes case, that is the only thing I think you need.
Are there other questions or remarks? Okay, if this is not the case, thanks Jacob again.
Thanks everyone.
Welcome back everybody to the last two talks of this afternoon. And the next speaker is Matthew Rosenzweig from MIT, and he will talk about mean field limits for systems of particles with Riesz interaction and possible noise. Please.
So, thank you very much for the introduction, and thank you very much to the organizers for the invitation to speak. It's a great pleasure. Sorry we can't all be together in person, but that's life right now. So today I'm going to speak about something that's perhaps a bit different from the other talks, which is not so much about the transport or continuity equations themselves, but how these arise as macroscopic scaling limits for systems of points that we can think of as interacting particles. So here's a brief outline of the talk. First, I'll introduce you to these microscopic models and what at least formally are their macroscopic limits, which are these transport type equations. Then I'll talk a bit about what we can say for proving mean field convergence for general systems with Riesz type interactions. So an inverse power, x to the minus s for some s greater than 0. And then I'm going to specialize to something which is perhaps a bit more technical, which is trying to prove convergence under minimal assumptions on the limiting solution, in particular that it only belongs to a scaling critical function space. And then finally, in time permitting, I'll talk about what we can say if we add some dynamics or stochastic noise to the dynamics at the microscopic level, and whether that persists and we get a stochastic partial differential equation as a mean field limit, or it somehow gets averaged out and we get a deterministic system. And then finally, I'll conclude with some remaining problems and thoughts for the future. So what is our microscopic model? It's given by a system of n ordinary differential equations, which is this system 1, 1. So xi is supposed to be the position, let's say, of the ith particle, and it's just moving along its velocity field given by this right-hand side. So there's a few things going on here. The first is that you have this constant real d by d matrix M, which we can take to either be antisymmetric, and this corresponds to Hamiltonian dynamics, or we can take it to be minus the identity, and this would correspond to gradient flow dynamics. And if you really wanted, you could take a combination of the two as well. Mixed flows are also permitted. So these particles are lying in RD for D, whatever you want. And this potential G, I'm going to focus on a model case, which is so-called Riesz interactions or log interactions. And we'll index it by a parameter S, which takes values between 0 and up to D, but not including D because that's no longer integrable anymore. It's important for this potential to be at least locally integrable near the origin. So the S equals 0 case corresponds to a log interaction. And for S between 0 and D, this is just an inverse power of the distance to the origin. And I'll call this sort of the Riesz case. And based on this value of S, when S is D minus 2, this is just the Coulomb potential. And when S is less than D minus 2, we'll refer to the interaction as being subcoulombic. And analogously, if S is bigger than D minus 2, we'll refer to the interaction as being supercoulombic. And then one final comment is that I'm only going to be focusing on so-called repulsive interactions. So the particles get repelled when they get close to each other. And that's reflected in the sign that's present here. Some comments about this model on a physical level. The first is that there's no self-interaction in this model. That would be infinite, corresponds to when J would be equal to I up here, which wouldn't make any sense. The other is that this interaction is long range. The macroscopic length scale is of order 1, but at the microscopic level, if you have n particles in a box, let's say of size 1, then the typical distance between them is going to be n to the minus 1 over d, which is much, much smaller than the macroscopic level. So each particle is interacting with many, many other particles. And then finally, the velocity field experienced by a single particle is just proportional to the average of the fields generated by the remaining particles, hence the terminology mean field. So this model has numerous applications throughout physics and other fields that I'm not going to go into. There's some excellent surveys, in particular the one of Pierre-Emmanuel Jabin, which gives numerous reference for this. But perhaps of most interest to this workshop are the connections to vortices in dimension 2 and in the Coulomb case. So if you have in the Hamiltonian case for the matrix, it's just a 90-degree rotation. This is the classical point vortex model. It goes back to Helmholtz and Kirchhoff, and famously was the basis of Onsager's statistical theory of 2D turbulence. And then in the gradient flow case, we also have these vortex models for Ginzburg-Landau as well that are of interest. So what questions are we actually interested in studying about these systems? Well, the first is, what are the limiting dynamics of the so-called empirical measure, which is given by 1, 3. You just take each point at time t and you place a Dirac at it, and then you average to get a probability measure. We want to understand what this converges to as n goes to infinity. Another question on a more statistical level you could ask is, well, suppose that the particles' positions are distributed according to some law, Fn, at time t. And we could ask, what is the limiting behavior of this law as n goes to infinity? And closely related to this second point is so-called propagation of chaos. It was introduced by Boltzmann and later refined by Kac, which is that if initially the points are independently and identically distributed, let's say with some law mu naught, and this just means that this initial law, the joint law of the particles Fn naught is an n-fold tensor product. Is it true that for positive time that the law of the particles is also factorized? In general, no, this is not going to be true for any finite n, but we can hope that at least on some sense that as n goes to infinity, this approximate independence hold. And more precisely, this is usually measured in terms of convergence of the k-point marginals of the system. And finally, I should remark that it's known that mean field convergence, which typically refers to proving a limit for this empirical measure, and propagation of chaos are closely related. And in fact, in some senses, they are equivalent to one another in a way that you could make precise. So how do we at least get a guess for what the limiting dynamic should be? Well, let's take the empirical measure and you test it against some function and take its time derivative. You use the equations, the system of ODE satisfied by these points, xit, and it's not a hard computation to show that as n goes to infinity, at least formally, the empirical measure should converge to a solution of the mean field equation given by 1/6, which is this nonlinear continuity equation here. So I have a scalar mu, and then the nonlinearity is this term right here, where I have this velocity field, or that I'll refer to as the velocity field coming from the interaction. And you can also show actually that the empirical measure is in fact a weak solution to this mean field equation as well. This actually has important consequences for how we go about studying these mean field limits, as I'll comment further later. And when I refer to establishing the mean field limit or showing the mean field limit, I always mean proving this convergence of the empirical measure to a solution of this equation 1/6. So there are numerous ways to go about showing this convergence. I mean, these problems have been studied for a long time. I think the classical method that was popularized in some lecture notes at Schnitzman is about comparing trajectories of the system to those trajectories that are determined by looking at the characteristics of the mean field equation. And this works quite well when the gradient of the potential is Lipschitz or even more regular, but it doesn't work so well when you have a less regular interaction, because if particles are coming close to each other, well, then this is going to become quite singular. And somehow you need to control the microscopic dynamics in order to prevent that, which in general is non-trivial. Another way of going about this is finding a good metric to measure stability of solutions to the mean field equation. And this exploits the fact that the empirical measure is in fact a weak solution to the mean field equation. And this is also, again, a quite classical technique. Often this is done by measuring stability in some Wasserstein distance. And then finally, a less commonly used technique, but I think also can be fairly powerful, is to use the so-called relative entropy by comparing the law of the particles Fn to the factorized law mu tensor n that you hope should at least approximately describe the dynamics for large n. And you try to prove a Grandwell relation for this quantity. This works well when grad G is possibly singular, but again, it can't be too rough. So many people have contributed to analyzing and proving these mean field limits. These earlier works, say by Goodman, Howe, and Lowe, Grubb, and Chauchet, were for the point vortex model, and they proved convergence under some rigid assumptions, for instance, grid-like data, or in the case of Chauchet, he has a sort of compactness argument, says you converge to some solution of the Euler equation, but in general, you can't characterize the limit points. And these results, again, don't imply, at least as far as I know, propagation of chaos. The next set of results concerns the subcoulombic case, S less than D minus 2, and these were proven via stability in Wasserstein distance, the W infinity distance. And then if you look in the 1D case, things are rather special because the Riesz case in one dimension is convex. And this is only true in 1D. And using this convexity and Wasserstein gradient flow techniques, people were able to treat the full range S between 0 and 1 only in dimension 1. Progress in higher dimensions, though, came in work by Mitja Dwerings, where he adapted so-called modulated energy method that had been introduced by Silvia Serfati for Ginzburg-Landau vortices to the study of the mean field problem for gradient flows. But again, this was only restricted to S less than 1. So it reaches the Coulomb case in dimension 2, and can in fact cover, but it doesn't cover the full subcoulombic case. And again, doesn't even reach Coulomb in dimensions 3 and higher. And then in a breakthrough result, Jabin and Wang showed that the relative entropy method can cover a large class of interactions that in particular includes the 2D Coulomb case for conservative flows. But in dimensions 3 and higher, it's more restrictive. And again, it works less well in the gradient flow case. Finally, this work of Silvia Serfati, the full Coulomb and supercoulombic case, either conservative or gradient flow, was treated in any dimension for the modulated energy method, which I'll say a little bit more about momentarily. But this again left open the question about the subcoulombic case. Can you treat that simultaneously? It doesn't follow from this result. And then finally, Brush, Jabin, and Wang combined the relative entropy and the modulated energy methods into this beautiful modulated free energy, which works extremely well for gradient flows and can actually treat the full range of interactions in any dimension. But again, it's very special to gradient flows, as you might guess from looking at a free energy. And it leaves open the question of the conservative subcoulombic case as well. So this leads to this first set of results that I want to discuss. And in order to tell you about them, I need to tell you about this modulated energy method. So the idea is to use a Riesz metric that's based on the interaction. And as I commented before, this was introduced in some work by Silvia Serfati, or the idea, I should say, was introduced work by Silvia on mean field limits for Ginzburg-Landau vortices. And it was first actually adapted to the mean field case for these first order systems by Mitja Dwerings in this work that I mentioned on the last slide. So what is this metric that we're looking at? It's this quantity Fn, which is given by this side over here. G is the interaction potential in our original microscopic model. How you should think of this, and I should say that also here I'm integrating, but I have to exclude the diagonal in order to make sense of these Dirac masses and remove the self-interaction. So how should you actually interpret this quantity? Well, if you forget about the fact that I exclude the diagonal, and you recall that G is corresponding to the inverse power x to the minus s, then this is really just a renormalization of the Sobolev norm h dot s minus d over 2, or the squared Sobolev norm. And the renormalization is carried out in order to remove the infinite self-interaction between point masses. This is a general theme throughout this talk, is that when you're dealing with singular interactions, you always have to renormalize to remove self-interaction, which is going to be infinite. So the idea of considering a modulated energy is actually somewhat classical. I think, as far as I know, it goes back at least to work of Brenier on quasi-neutral limits for the Vlasov-Poisson equation. It also has similarities with the relative entropy method, which again is classical for proving stability of conservation laws, has also been widely used in studying hydrodynamic limits. This method relies heavily on a weak strong uniqueness principle for the limiting mean field equation. Its advantages are that it's quantitative, and in particular that you don't need to have a detailed study of the microscopic dynamics, which in general is rather non-trivial to do. But its disadvantages, at least historically, is that it's required some regularity for, or an a priori assumption on the solution to the limiting mean field equation. Although we'll see in the next section that this is not always the case. So the result that we were able to obtain with Hung Noon and Silvia Serfati is able to prove mean field convergence for the full range S between 0 and D, so subcoulombic, coulombic, supercoulombic, and in any dimension, and both for conservative and gradient flows, under some assumptions on solutions to the limiting equation. Namely, we need assumption, which is a measure. It's also an L infinity, at least locally in time. And in the Coulomb case, we need that the Hessian of the potential is an L infinity. So this corresponds to a Lipschitz assumption on the velocity field. And in the subcoulombic case, there are some additional regularity assumptions from UT that I'm not going to specify here. I should comment that actually this first assumption you can remove in 2D. And I'll say a little bit more about that when I talk about convergence in critical spaces. So our result is quantitative. We have an explicit estimate for the evolution of the modulated energy, which is given by this expression here. C is some constant, which depends on norms of the limiting solution that you can control in terms of initial data. Beta is some exponent as well, which is given by all the parameters that you can write explicitly. And then of course I have this Gronwall time, this time dependence going from Gronwall, which in general will degenerate for very large times. So one consequence of this is that, well, if I have weak star convergence of my initial sequence of empirical measures, and I also have a convergence of this modulated energy at initial time, and this will imply weak star convergence of the evolution of the empirical measures to the solution, unique solution of the limiting equation, locally uniformly in time. So some comments about this result. Well, the first is that this convergence of the initial value of the modulated energy is a well-preparedness assumption. It's rather mild. It's implied by convergence of the normalized microscopic energy here to the energy of the limiting equation. This regularity assumptions also allow, for instance, in the Coulomb case, for patch solutions, things that are L infinity solutions, which are level sets of functions, so vortex patches for the Euler equation. And as I commented earlier, in the 2D Coulomb case, you can get rid of this assumption right here and just assume that mu naught is an L infinity. So you just need to be bounded. And again, these regularity assumptions on this theorem is not vacuous. The regularity assumptions for the limiting equation are satisfied. This has been shown in works by a bunch of people. So I won't read out. And then finally, this theorem is not just specific to Riesz interactions, the model case, but it allows for more general Riesz type potentials. And I think one should compare this result to this aforementioned work of Bresch, Jabin, Wang, which one of the advantages of their technique was that they could also allow for more general interactions than just the model Riesz case. So how do we actually go about proving this? Why is the modulated energy a good metric for measuring convergence? As I commented earlier, this is in some sense a squared h dot s minus d over 2 norm, but due to the exclusion of the diagonal, it's actually not clear that this is non-negative. In other words, that's coercive. But in the Coulomb case, if I smear out each of these Diracs that are appearing here to a uniform measure on some sphere of some small radius eta I, you can show that actually the modulated energy is bounded from below by the h dot s minus d over 2 norm. There's a typo here. There should be delta xi eta I appearing here, minus mu, and then some error term, which is coming from the smearing that you can quantify. So this actually works outside the Coulomb case and the supercoulombic case as well, a highly non-trivial extension that Silvia introduced based on the Caffarelli-Silvestri extension method for the fractional Laplacian. But it wasn't clear how to extend this as well to the subcoulombic case and treat more general interactions. So one of the contributions of our work is to introduce a more robust smearing procedure, which is based on the fact that in the subcoulombic case, the potential is superharmonic. So Flaschen is less than or equal to 0. Outside of in the supercoulombic case, this is no longer true. But if you observe that the potential is the restriction of this function g, where it's just the same inverse power, but in a higher dimension, if I choose k large enough, I again restore superharmonicity. And so you can perform a smearing procedure, but in an extended space as well. The next sort of key component of this is to actually estimate the right-hand side appearing when you compute the time derivative of the modulated energy. So it's not too hard to show that you reduce to this differential inequality given by 210, and you somehow need to bound this right-hand side here, where I've introduced some notation u, which is corresponding to the velocity field from my model. So how should you think about this expression that's appearing in the right-hand side? Well, I claim that this has the structure of a commutator, more precisely a commutator which has been renormalized to accommodate the singularity of the Diracs. If I pretend for a moment that this is regular enough, and I just call this f, and I rewrite my left-hand side in the form given by 211, this is nothing but this dualized commutator estimate given by this right-hand side. So I should expect some sort of smoothing effect coming from the potential right here. And also, this suggests a connection between proving estimates for these quantities, these expressions here, and singular integral estimates and paraproducts and harmonic analysis theory that are used to treat commutators. So this is the result that we have. We can bound these expressions in terms of the modulated energy plus some small error, provided that we have control of the gradient of the velocity fields. This is where this Lipschitz assumption is coming from. So in the Coulomb case, these estimates are proved using a stress energy tensor structure that's implicit in this left-hand side. This is similar to the stress energy structure, tensor structure that appears in Delort's work on vortex sheets. And again, you do a non-trivial extension to show that such a stress energy tensor structure also exists in the supercoulombic case as well. But reliance on sort of stress energy arguments is rather rigid. It's not clear how to generalize this to the subcoulombic case and things that are not inverse powers as well. So we forget about that. And instead we introduced a robust harmonic analysis methods in order to estimate, to prove functional inequalities of this form, and in particular to draw a connection between commutator estimates. So what's the flavor of this? Well, let's just write f as the divergence of some vector field, f1, and we rewrite the left-hand side, the functional inequality, so this expression here, in this form here, where I've introduced some notation k for the kernel appearing, coming from my interaction. And then I divide into cases based on the value of s. So in the supercoulombic case, I integrate by parts. I do some symmetrization, paying attention to the diagonal, and I can show that this is bounded by this expression here. And then if I recall my functional analysis, I see that this is nothing but Sobolev norm of f1. And then I recall what the original definition of f1 is, and the fact that its divergence is just f, and use Poincarel's theorem and reduce to this expression appearing in the right-hand side. For the Coulomb case, the idea is similar, but we need to work a bit harder because the Sobolev semi-norm trick is no longer valid. And instead we rely on singular integral estimates, particularly the L2 boundedness for so-called Calderon decommutators. So a class of singular integral operators that were studied some years ago by Krista Jornet. And then finally, in the subcoulombic case, well, the idea is to iterate this integration by parts and some other ingredients that go along, and then reduce to one of the two previous cases. So I've cheated a little bit, which is that implicit in this reasoning, I'm assuming that f is regular enough, in particular for this expression here, the Sobolev norm, to make sense. But of course, this is not necessarily true if f is just, the empirical measure minus the solution of the mean field equation. That's too singular. So in fact, in order to apply any of these estimates, we need to renormalize our original expression by smearing the Dirac masses to an appropriate scale. So this is where the smearing procedure that I mentioned before really comes into play as well for proving these functional inequalities. So how am I doing on time? I forget when we started.
I think you have still 20 minutes.
Okay.
Maybe more, actually.
No, I would say something like 5 and something. So it's due until 5 and we started 5 minutes later.
Okay, so about 5 minutes. Okay.
So, no.
So all right.
Okay, sorry.
Let me just say a little bit about the scaling part. I don't think there'll be time for the noise, so you can ask me questions about that if you're interested. So, okay, we've seen how to prove mean field convergence under some assumptions, but again, they can be somewhat restrictive, or they could be demanding on the amount of regularity that we need for solutions to the limiting mean field equation. And we can ask, well, what are the minimal assumptions that we actually need to impose in order to prove convergence? And let's focus for a minute on the 2D Coulomb case. Either conservative or gradient flow, it doesn't matter. So this is a log interaction. So I've just specialized it and got rid of the notation G. And you can compute that this equation is invariant under the scaling given by 3,2. So I just replace x by lambda x for some positive parameter lambda. So as you can see, the scaling leaves the L-infinity norm unchanged. In other words, L-infinity is a critical function space for the well-posedness of this equation. Moreover, in the Hamiltonian case, the L-infinity norm is conserved. It's a Casimir for the Hamiltonian structure. And in the gradient flow case, it's decreasing. So also, we know that this equation is globally well-posed if I have a measure, which is also an L-infinity. But there's a problem though. If I think back to the estimates I showed you before, they all involved control on the gradient of u, which suggests Lipschitz. But in general, for L-infinity data, the velocity field is only going to be log Lipschitz. So there's a gap between the two. This leads us to the following question. Can we assume, or can we show mean field convergence, assuming only that the initial datum is a measure, which is an L-infinity? So in particular, this would allow for non-Lipschitz velocity fields, and it would require no regularity for the limiting solution. Again, there's a gap between what we want to show and what's been proven in the literature. You have this early work of Chauchet, which is proving convergence for measures, so things that are very rough, but there's a price that you pay is that you don't actually characterize what you're proving convergence to. And also you can't deduce propagation of chaos from this result as far as I know. So in some sense, it's incomplete. And again, the best result that I know of for the regularity requirement on the limiting solution is by this previous work of Sarfati, which says, okay, you can be an L-infinity, but you still need your velocity field to be Lipschitz. So this leads us to a result of myself from a year and a half ago, which is that L-infinity is okay. You can have a L-infinity weak solution to the mean field equation, which has finite energy and doesn't grow or decays fast enough at infinity, and you can prove a quantitative bound for the modulated energy. And in fact, you don't actually need to be L-infinity. You can be an LP for P large enough, provided that you have control in the log Lipschitz semi-norm of your velocity field. So the key behind this relaxed regularity requirement is refining our functional inequality that we have, this renormalized commutator estimate that I introduced before. And in particular, so this is sort of the workhorse of the expression. It's rather a mess. These parameters epsilon, epsilon2, epsilon3 are introduced to measure various slack that you have in your estimates. You can forget about everything that's appearing here and just focus on this first term. So I had the modulated energy, which is good because I want to apply Gronwall. But then I have this log epsilon2, which is bad because if epsilon2 is supposed to be small, then this expression is going to blow up. So this estimate is proven through a mollification argument. There's several steps to it, but I think the key idea is that I want to mollify my vector field, and I want to use the log Lipschitz regularity of V to bound the error from replacing V with V epsilon2. And then I want to proceed with working with the epsilon 2 as far as I can. So I avoid any estimates that require Lipschitz control, but there's one price where I cannot avoid this. And when I estimate the Allen-Free norm of the gradient of the epsilon 2, I pay this price, which is this factor of log epsilon 2. But it turns out that if I choose my epsilon, epsilon 2, epsilon 3 carefully enough, in particular to depend both on time and the number of particles through the size and the modulated energy, I can take that functional inequality they proved before and arrive at an integral inequality of the form 3/7. So I have my modulated energy, it's controlled by its initial datum, some perturbative error, and then this expression here. So this is almost good enough for Gronwall, but I have a log factor. But I can still close my argument because this still satisfies the Osgood lemma. And this allows me to prove the bound on the modular energy that I stated before. So you can push this a little bit further to the Coulomb case dimensions 3 and higher, but there's an inefficiency which only allows you to show it for short times that are perhaps smaller than the lifespan of the limiting solution, but still of order 1. And then some work in progress is to generalize this for arbitrary times and for the full Riesz case, S less than D, by better using the regularity of the velocity field. So I think I'm out of time. So let me skip to the end and say that there are a number of questions that remain. In particular, we had asked what are the optimal timescales and size of error for the mean field approximation. And then lastly, everything I've told you about is for first order systems, but I feel like I would be omitting an important truth if I didn't say that I've been strongly thinking about second order systems, which in general are rather interesting, very interesting, because this corresponds to the so-called Blois-Poisson, but again, much harder because you have to deal with the velocity, controlling the velocities of the particles as well. And with that, I'll thank you for your attention and happy to take questions.
Okay, thank you. And okay, so I think we have time for some quick questions, please.
I have a very naive one. So how much of this survives if G has so this potential G has the same blow-up behavior, but not the exact expression that you're considering?
Or
is that rigid? Or?
So it doesn't need to be an inverse power. So you can allow for it to sort of blow up like this. The short answer is a good chunk of it survives if you sort of allow it to have this blow up. The important ingredient for us to be able to generalize, to allow for that generalization, is that you preserve superharmonicity of G in the subcoulombic case near the origin. It just needs to be local in some radius of size 1 near the origin. And in the supercoulombic case, you need your potential to admit an extension to some higher space such that that extension is superharmonic. But it doesn't, you could allow for things which are blowing up like x to the minus s, and you also need some control on the Fourier transform as well, and some control on how the gradients decay or gradients blow up as well. But that would still be okay.
Thanks.
Okay, there is another question.
Hi, Mas. May I ask? I'm Franco.
Hi.
Yes, I would like to know if the noise you use is independent for every particle, or you have common noise. What kind?
So both are okay, actually. Okay. Yeah, everything I said in the first part was about deterministic systems. But yeah, so we could have for independent, so the additive noise case where you have an independent Brownian motions affecting each trajectory, and then the multiplicative case, like in your work with Gubinelli and Priola. Yes. So for this multiplicative case where you have common noise, the subcoulombic case and the Coulomb case are fine. We can prove convergence. the supercoulombic case, so we have all the estimates for the modulated energy method, but I don't know, you could answer this question better than I could. I don't think the regularity for the limiting solutions to the stochastic PDE are known. So in that sense, the result would be conditional on whatever theory you had for solutions to the stochastic PDE. For the independent noise case, we only know how to treat the subcoulombic case. So dimensions 3 and higher and S less than D minus 2. So we barely miss out on the Coulomb case. But I think the nice thing though about what we can say for the independent noise case is that our convergence results are actually uniform in time. So there is no, none of this e to the CT factor. The bounds hold for arbitrary time on the real line. But that's very specific to the independent noise because you have this dissipation in the limit, which gives us some decay.
Thank you.
Yeah, sure.
Thank you. So let's start with the last talk of this afternoon. The speaker is Igor Mencic from the University of California at Santa Barbara, and he will talk about, the title is From Control of Mixing to Mixed Norms, Mesohyperbolicity, and back. Please.
All right. Thank you very much. First of all, thanks to organizers for inviting me. I had a chance to look through some talks in the last few days. It seems like it's a wonderful workshop, and I'm really sorry that we're not together to exchange information. I'm sure everybody starts. I mean, I see everybody starts their talks with that particular sadness. But I'd like to concentrate today on actually a specific question. My title is somewhat long because there are a number of tools that I'm going to present in trying to resolve this issue, but it's an issue that bothered me since literally I was a graduate student, which was a long time ago. And that is that we had very good tools to understand mixing in laminar flows. And then when we would go to, and these were deterministic tools from dynamical systems theory. And then when we would go to turbulent flows, we somehow lost that power to describe things in detail using dynamical systems theory and had to change the tools. So over the years, we've developed some set of methods to try to understand how to go to that higher Reynolds number side, and that's what I'm going to be talking about today. So just a few remarks on mixing in general. As you know very well, mixing is really an all-important subject. Interestingly, at the same time, it's a deep mathematical subject. For example, vertical mixing in the ocean and atmosphere is a big issue today in the context of climate change, and understanding it better, it really hampers the lack of understanding of it really hampers our ability to project even further in the future and understand what is going to be happening to the climate. Not to mention all the pollution and the aspects of. Can you see my cursor actually as I move it around?
Yes.
Okay, very good. So not to mention all the aspects of pollution and the need to try to understand where the pollutants end up when we either accidentally or just by normal production deliver them to the sea. But there are other examples. Mixing in the earth mantle is a very important topic. Blood flow mixing in relation to health and disease. Role of mixing in shaping the ecological equilibrium and so on and so forth. There is another topic which is control of mixing, and in natural flows very often, most commonly we cannot pursue that, but in industrial flows we can design mixers for a variety of different purposes, and so the control of mixing is also an interesting topic in general. So as I said, mixing for laminar flows is characterized very well. Now, the theory of chaotic advection started in 1984 with RF's paper. One could argue that it was even earlier with Arnold's and No's work, but after 1984, it really became a big topic of investigation. By the end of 90s, we understood this very well, both in two-dimensional and three-dimensional flows. But then when one goes to theory of mixing for turbulent flows, that's largely rooted in statistical physics. So there is really a dichotomy between the set of tools that are being used between these two. And so today I'll present a theory that allows for study of both. And while I mentioned dynamical systems theory as a route for studying mixing in laminar flows, here I'm going to rely on ergodic theory. Now, ergodic theory, of course, is part of dynamical systems theory, but it's a specific part of dynamical systems theory that deals with statistical properties of dynamical systems. And so via this ergodic theory approach, this statistical physics approach in dynamical systems theory can actually be joined. That's maybe a higher level description of what the approach looks like. The other aspect is that what I'm going to show you today combines Lagrangian Eulerian elements. Mixing is here treated in laminar flows in this particular theory, treated as a Lagrangian subject. We get the velocity field and then proceed with the Lagrangian aspects of it. You will see that in the theory that I'm going to describe today, there is a combination of Lagrangian and Eulerian elements. The key ingredients are spectral expansions of the Koopman operator. So I will go ahead and define the Koopman operator itself. And then mixed norms, which I'm really going to spend relatively short time talking about today, because they're going to be useful for me to compare certain aspects of Lagrangian dynamics. The mixed norms are in themselves a much broader topic today, since we introduced them back in 2005. And then mesohyperbolicity, a concept that is going to enable us to visualize mixing dynamics in three-dimensional flows. Now, I'll finish with Koopman operator theory for control of complex systems, such as turbulent fluid flows. And kind of that's the outline of what I'll do today. So because a lot of this relies on a specific aspect of ergodic theory that Koopman and von Neumann have formulated, it is an image, a video from this paper of Rowley, myself, and collaborators in 2009, where you're seeing a jet coming out of an orifice. And this particular example, in fact, comes from practice of designing jet engines. One cools the walls of the jet engine using a colder stream of air coming from the side of it. But that means that jet is also perturbed by a flow coming from this direction. You can also see something like this with a smoke coming out of a chimney. You've probably seen a picture like this many times. The reason the video is here is just to show you using these contour. The red is the contour of streamwise velocity. So it's the contour of one constant, one level set of velocity in the streamwise direction. And it's there really to just point out how complex the underlying flow is. So the idea of introducing a Koopman operator for this particular setting, in this case, the underlying dynamics is Navier-Stokes equation, is to introduce a linear operator. I give an infinite dimensional linear operator on an infinite dimensional system. So of course, the technical issues that I'm going to be talking about next are something to worry about and resolve. But then its power relies in the fact that it is a linear operator. So if one has ways of finding eigenvalues and eigenvector, eigenfunctions, then one can actually talk about decomposing that into simpler ingredients. And indeed, for this one, what we could compute is a unit circle in the complex plane. So we could compute pairs of eigenvalues of that operator. You're seeing them in a brighter red color here. And the associated modes, or call them Koopman modes, is what comes. And you see that these underlying modes are, the contours of these underlying modes are much simpler than the contours that you're seeing over here. And yet, these are the basic ingredients of what you're seeing over here. Now, for those of you that might have studied turbulent fluid flow in jet and cross flow, you might be recognizing some of the features. The horseshoe vortice is here, the ring vortice is on the jet, the stringwise vortices. All of these are physically known and understood, but they are an essential part of what I'm going to call spectral decomposition of the Koopman operator. So I wanted to convey the basic idea early, so that we have some kind of anchor. The idea is to decompose the system in its simpler components if possible, and I'll mention exactly where possible and where not, and then study those simpler components. So this comes from a reformulation of dynamical systems theory in terms of what is called evolution of observables. Koopman and von Neumann used it classically to study measure preserving systems. If you look at the mathematics literature for a long time, even before Koopman, the underlying operator was called a composition operator. And what we are interested in is spectral theory. So spectral theory of these operators. The reason why it's used quite a bit today in a variety of fields is that the relationship to data analysis is very direct. So it's akin to stochastic process theory, but it does speak about coherent structures rather than spectra. Very happy to discuss any of these because some of them, because of the focus of the talk, are slightly vague. So if anybody wants to ask question, would like to ask me a question at the end as to what I meant with any of these, I'm happy to do that. Okay, so just a brief background on Koopman operator theory. Instead of states, so for example, velocities in the fluid flow, it deals with observables on the phase space. So F can be velocity itself, but it could be a variety of different functions of velocity, for example, energy. The Koopman operator itself is a composition operator. So if you have a map T from M to M, and you have an observable F, then U acting on F is F composed with T. In the continuous time, UTF is F composed with STX. We are assuming here existence uniqueness, of course, something that we don't have, generally speaking, in 3D for fluid flows, but under assumptions of existence uniqueness, this is well defined. This goes back to Bernard Koopman and von Neumann, so to some luminaries of the early and mid 19th century mathematics, and also Carleman came up with similar ideas in 1931. Koopman was the first. Carleman did realize, somebody told him about that paper, so he mentions Koopman, I believe, in his 31 paper. That there was an interaction there. And just to kind of give you an intuition of what the transition in the point of view is, if we started from x dot is f of x, which is some finite dimensional vector field, possibly with some control term here, a of xu, but let's neglect the red for a second, then our equation for evolution of f would be essentially a backwards advection equation, right? So this is the dual, so it's partial f with respect to t is f of x dotted with grad f. So if you transfer it to the other side, we have a minus sign. So it's not an advection equation. Well, it's not a forward advection equation. It's a backwards advection equation. And so the Koopman, when Koopman operator transforms functions, it looks at a point and receives the information backward. So it's really a Lagrangian point of view in fluid mechanics terms. And the objects that we are going to be most interested with is if we take the right-hand side of this equation and extract f of x dot grad f, then the functions phi that satisfy f of x dot grad phi is lambda phi. They're called, they're obviously eigenfunctions of the associated operator f dot grad. And this f dot grad is the generator of the evolution under the Koopman operator. So this is in a nutshell and basically a crash introduction into eigenfunctions. Well, the operator evolution itself, the generator, and then the associated eigenfunction. Of course, in continuous time case, the evolution under the operator of function phi is e to the lambda t phi, if phi is an eigenfunction. Okay, so yeah, this is the generator equation. This is the eigenfunction equation, and so what is interesting here is then the geometry of level sets of Koopman eigenfunctions in state space. In fact, give us interesting information about the Lagrangian aspects of the dynamics. The Koopman, it's not Koopman, it's Koopman modes are projections on Koopman eigenfunctions. That's a strict definition. So if you find an eigenfunction and you have some physical field like a velocity field, one can project that velocity field on that eigenfunction and obtain a mode, and they play a substantial role in Eulerian dynamics. And so really it's the coupling between these eigenfunctions and Eulerian dynamics that plays a substantial role in what I'm going to say today. One last thing, in the case you're wondering, is I'm defining an infinite dimensional operator on an, if I'm dealing with Navier-Stokes, an infinite dimensional operator on an infinite dimensional evolution. And the question might be, well, how do I compute here? There are several answers to this, and if we didn't have answers to this, I believe this would still be within the theory realm only, not computation, but we do have a number of different computational methods to do this. I'll show you a couple of those, especially if we want to just define spectral elements that can be done without exhibiting the operator. All right, so perhaps perhaps the most important type of result in Koopman operator theory is then an expansion into Koopman modes. The reason being, as I've shown in that movie right at the beginning, that Koopman modes can simplify the understanding of, in principle, very complex dynamics. Even within chaotic dynamics, we have found that there are pseudo eigenfunctions that, in fact, are quite coherent. So the type of result that I'm showing here exists for many different functional settings. The simplest setting is the classical ergodic theory setting. So in case when the flow itself, ST, is on a compact metric space, and then the function G is a vector valued function. Think of it as velocity field physically. So the vector valued function G, that is a function of Z and X. Z is the point in state space, and X is the point in physical space. So it can be expanded into what is classically called the singular and regular part of the operator itself. So the operator can be split into its singular component and regular component. The quote-unquote singular component, this is classical terminology, has point spectrum and an associated invariant subspace. The regular component has continuous spectrum. Now we can further split the singular component into the mean, and this star here is actually going to indicate time averages. The mean, think of this part in a fluid flow as the mean time average of the velocity at any given point. So all the velocity components. Then this part here, that provided the flow is on the attractor, lambda j's are going to be I omega j's, meaning purely imaginary. So this is this lambda j here is an eigenvalue of the Koopman operator. You don't see that over here because the associated eigenvalue is 0. So e to the 0, of course, is 1. So the mean is there. This is the quote unquote oscillatory part. It's really the quasi-periodic part. And then this part here is comes from the possible existence of continuous spectrum. So if you think about something like Lorentz attractor that is mixing, that has only continuous spectrum, so it would be only this part that would exist. If you had a system that had a fixed point, then it is only this part, or limit cycle, or a toroidal attractor. Now, this term here, as I said, is a projection of G on the eigenfunction. This is the complex conjugate of the eigenfunction, and we are going to call it Sj, and that's what's today called a Koopman mode. That was derived in this paper here in 2005 for the first time. And then this is an eigenfunction and eigenvalue. So usually eigenvalue, eigenfunction, and mode are called the spectral triple. So the three spectral objects that pertain to the evolution. The eigenvalue and the eigenfunction are the properties of the operator. Sj is the only part that has G in it. So it depends on the observable you're looking at. So for example, if you're looking at the temperature in a fluid flow, that object, that Sj would be different in this expansion. And then this pertains to the chaotic part of the evolution if you have an ergodic attractor. There is a precedent in fluid mechanics, a heuristic precedent. There's the so-called triple decomposition of Hussein and Reynolds. If you actually look that up, it contains some of these ideas that can be certainly rigorously exhibited in the context of the Koopman operator. Okay, so now we're going to concentrate on various parts of this in order to understand mixing. So we're going to start with the eigenfunctions, and we're going to presume for the next few slides that we know the velocity field itself. And we're going to talk about the eigenfunctions of the velocity field. And as you could see in the decomposition, there is this part that is the mean. But very often, if you have a map like this one, so this is the famous standard map. If you looked at its trajectories, here is the state space between 0 and 1 here and 0 and 1 there. And you're seeing some coherent trajectories that are kind of circling around, but you're seeing some that might be filling the space in a positive measure sense. So those would be chaotic trajectories. There is no proof for this map in it. It is a very similar map that has instead of sines, it has piecewise linear parts. It is Arnold's conjecture that we have volume filling trajectories here, and that hasn't been solved since, I believe, 1965. But there are some very similar maps in which you can prove that there is a mixture of regular and chaotic motion. And so what this theorem here says, that you might wonder, well, if I have these trajectories, what are really, and I have volume filling trajectories, what is really a fundamental object? Is it really the trajectory, or really the volume, the area that the trajectory fills? And of course, the answer is the closure of the trajectory is the object you should be talking about in this sense, especially if you're talking about mixing. And so it is a theorem I did a while ago that says that if you put a basis of observables on this space, so going to Koopman point of view, and you find the time average of each of these functions fi in a basis, then the ergodic partition, which is the partition into finest invariant sets of your state space, is a product of partitions that are induced by individual functions fi. So practically speaking, you take a bunch of functions in a basis, you find the time average of each of these functions. That's a new function, because starting from a different initial condition, you find a different time average. And then you find joint level sets of those time averages, and you produce a figure like this. And this one should somehow resemble that one, although you might see a lot more details and maybe understand the structure a lot better. So what I wanted to point out with this slide is that you can go from this very abstract observables-based point of view, and not from a pure Poincare trajectory point of view. And you can get back the geometrical objects that that Poincare looked for from this analysis in a way that is computationally quite simple, I would say, because you just run trajectories and find time averages, and then you find broad level sets. And that's kind of the whole point, that by doing the changing the point of view, you're actually getting these objects that one can get both numerically the handle on, and by the way, time averages can be obtained from data directly. So that's one big benefit. While you can't always get the state space variables from data, because you might be observing something different. So for example, you could be observing temperature but not observing velocity, and the time averages themselves can be obtained from data. So the time average is defined for a function f is defined just as a limit when t goes to infinity, 1 over t, 0 to t, f composed with phi t. This is really the flow. So this whole thing is, in fact, to make the connection to the Koopman operator very, very vivid, this thing here is really ut f. So indeed, it's an average of the action of the Koopman operator on the observable over time. Okay. By the way, if there are any questions along the way, please let me know. I can probably see them in the chat, I presume. So let me continue. Now that I've defined this, one can actually put this in quite a nice form. This is joint work with Marko Budisic, where these time averages are associated with invariant measures in a weak sense. So these mu x are invariant measures, and each fk you can think of, each f star, each time average you can think of as a moment of an invariant measure. And so if you have a basis of functions f, you can put these moments into a sequence. And so each point x in state space is now associated with a sequence of time averages. And it turns out that the previous theorem just says, if that sequence is equal to 2 points x and y, they belong to the same minimal invariant set, minimal ergodic set. And that gives us the ability to take a look, to metrize, in fact, the underlying space by utilizing a difference between the measures. And in this case, since we have measures characterized by their moments, then we use something that is akin to, I think a number of you might know the concept of the mixed norm. It's really a negative Sobolev space norm. Here we are comparing different measures for different points in the state space, using the moments and penalizing by k, which is the mode, which is the Fourier coefficient number, and we can choose power s here. These are in the class of negative index Sobolev spaces, and so a variety of different structures, invariant structures in the state space can be understood using this concept. For more, there's this paper that we've done some time ago. We can go further than that. We can identify underlying objects or sets in the state space that provide us with periodic partitions. So that's a little bit of a refinement of the invariants that you're looking at here. Here are the Poincare maps or trajectories And here are the plots obtained with trajectories using time averages. And here, instead of time averages, we use quote unquote Fourier averages. So instead of taking just a pure average, we weight with e to the minus I omega t for some omega. And if that omega resonates with the motion in the state space, then you get a non-zero object on the left-hand side, and you actually visualize structures or extract or produce partitions in the state space that are physically meaningful from a Lagrangian point of view. So from a Lagrangian point of view, the first thing that you would like to find out is the invariant sets themselves. And then the second thing that you would like to find out is the behavior inside those invariant sets. And this is what these types of averages allow you to do. So one can apply this in pretty complex flow situations. This is a work with Thomas and Alexander Fabregat Thomas and Andrew Poggi and some other collaborators. And here you're in this axis, this is time, and in this axis, this is depth, and this is really the Gulf Stream flow field evolution. And what you're seeing in different colors is essentially different measures, those mu x's that are supported on different sets of initial conditions. And one interesting thing that you see is this blue thing here. You can think of it as a vortex. And as we go to the right, you're going to see that it entrains another measure or another bulk of fluid and becomes a dipole. So by what I've just shown you, over finite time, you can visualize this process of a vortex entraining a volume of fluid and becoming a dipole. The underlying visualization is provided by clustering of invariant measures. So there is a little bit of data analysis with it. And so if you go to depth, to a little bit further depth, you can actually see that that dipole was there and kind of propagated. And then on the further depth, it in fact disappears over time. And so presumably if we went further time, this would also dissipate. So the point of this slide is that you can utilize this idea of comparing invariant measures that I had on this slide perfectly happily over finite time and not over infinite time, and have some really nice physical results for ocean flows. Now let me extend this a little bit further, and because I spoke about eigenfunctions. Now the modes are projections of eigenfunctions, and so you would expect that I could compute them by similar methods. And indeed, I've shown you actually two different aspects of computation of invariants or eigenfunctions of the Koopman operator. These are time averages are invariants at 0. The Fourier averages are invariants at I omega. So in fact, when you have a dissipative system, you can take arbitrary lambdas. They don't have to be e to the 0, which is 1, or e to the I omega. You can take arbitrary lambdas, and if you form this compound sum, it's really a time average of an object that contains a subtraction of the objects that you have previously computed. You get an exact formula for computation of Koopman modes. I'm not going to dwell on this too much. If there are further questions on how to compute, please let me know in the question period. But there are some functional space aspects of this that I would have to expand on just to describe it a little bit better. The other way of computing is really exhibiting a finite section of the Koopman operator. So a projection, Pn is a projection on a finite set of functions. And then interestingly, these elements of the finite section, so now the operator becomes a finite matrix. Interestingly, these elements are in fact time averages themselves. They have time averages of functions in the basis. One pleasing feature here is that you can literally plug this into MATLAB and compute. The reason being that these time averages here can be exhibited as using just the data matrix F. The data matrix is just the sequence of snapshots of your field. So for example, this could be the velocity at time 1, velocity at point 1, velocity at point 2, and so on and so forth, evaluated at different points in the space. So you get a data matrix. You can actually produce these elements of the finite of the finite section using this expression where F dagger is the Moore-Penrose, where this is the conjugate Hermitian transpose of F. So let's go and see what that now enables us to do. So here I'm showing you a solution of Navier-Stokes equations in 2D. The evolution is driven by the lid being dragged on the top, and so you're seeing the flow just circling around. This is vorticity that is being depicted, so you're seeing some swirls of vorticity happening. And so if we decompose this flow, we get the first mode, which is the time average. That's the mean flow, and you're going to see quite a bit of similarity with some moments in evolution, but not always, right? The last moment seems very similar. Now the mode 2 has this interesting periodic structure near the walls, and then mode 3 looks similar to mode 2, but even more refined. And the Koopman spectrum resembles the Fourier spectrum in that it has the first frequency and then the harmonics that correspond to these different modes. And the idea is that the sum of these modes in that formula that I gave you before gives the full flow. And this is at Reynolds number 13,000, at which the dynamics is periodic. So it's nice to ask the question, well, what happens with these decompositions when the Reynolds number becomes larger? At 16K, you have another frequency coming into the picture, and so you get a quasi-periodic spectrum. At 20K, you get something that looks like a mixed spectrum. We have evidence that it might be a combination of singular continuous spectrum, so not absolute continuous spectrum, and point spectrum. There is no proof of this, but we've designed methods with Mihai Putinar and Milan Korda to understand when this could be the case. And then at 30K, you're seeing a pretty flat spectrum. And that is an indication of the fact that we have a chaotic attractor. But it's interesting to look at the modes. So you can compute Koopman modes for each of these. Here is the mean mode. And what is remarkable, it doesn't change much with the change in Reynolds number. When we first saw this, we were honestly slightly shocked. It was really interesting. Now look at the second mode, and with some details, of course, change, but they look very, very similar as you increase the Reynolds number, and so on with the other modes. And remember, we're going all the way from limit cycle to chaos through something similar to Ruel-Takens scenario. Now, okay, let's see how this really works. So this is one mode plus, so mean mode plus mode 2, and you get something like that. That looks like the flow. Now, if you take 20 modes, you're in great shape. Compare 20 modes with the full data, and by per eye, I don't think you're going to see much difference. So the approximation is very good, and this is 20,000, Reynolds number 20,000, so it's aperiodic. So this is supposed to give us a feeling that for these types of flows that are at least transitioning to turbulence, we get a good decomposition out of it. You could ask, well, how about POD? And that's a really interesting question. As long as there are, so these are the plots where you have the number of modes versus the normalized error. And so, of course, both POD and Koopman mode decomposition are going to do well when you take enough modes, because in the limit of n goes to infinity, the reconstruction is perfect. But what's interesting is that, and this is a log scale of error, what is interesting is that for the flows with coherent structures, the Koopman mode decomposition does quite a bit better, Now, when you have Reynolds number 30,000, the POD and the proper orthogonal decomposition and Koopman mode decomposition are quite similar. And that makes a lot of sense. Actually, in the 2005 paper that I wrote, the interesting bit is that I said that the interesting bit is that the proper orthogonal decomposition was really originally designed by probabilists to treat systems with continuous spectrum. So they actually had in mind these types of decompositions. If you actually look at Carhoon and Leve book, when they start doing the POD, they actually say specifically, let's suppose that we have a system with continuous spectrum. So, so for unstructured flows, it makes a lot of sense to use POD, but one should certainly look for structures first. And some of the latest results that we have is that even in the systems that are mixing, like Lorentz system, there is quite a bit of structure that you can extract Koopman pseudo eigenfunctions. That's a bigger topic, but I hope this was a worthy comparison. The last thing I'm going to talk about, because I think I do have 5 minutes, right? Is that?
Yeah, sure.
Okay. The last thing I'm going to talk about is I'm going to bring us back to mixing and say the following. If you recall how I looked for invariant structures and then I looked at the structure within invariant sets. So I'd like to introduce another concept, which is the following. We're going to follow the trajectory. The vertical axis you should think of as time, and this is space. And we're going to follow this trajectory in the map that goes from x0 to that. And then we're going to try to ask whether around it, the material has hyperbolic properties, so it kind of stretches and goes away, or just spins. So these are the mesoelliptic and mesohyperbolic. So on average, do they spin and or have some kind of saddle property to them? You can test it on very regular flows that are just circling around, like the one that I've shown before. And you get these green zones in the middle, which indicate rotation, and then you get these blue zones on the side that indicate hyperbolic stretching. And then these ones in red are somewhere in the middle. They're neither nor. They contain both rotation and stretching. Now, when you do it on a flow that I've just shown you, you see that close to the walls, there is a lot of mixture of blue and red. And in the middle, it's all green. So if you actually saw that flow with a naked eye, you would actually probably told me that there is just seems like pure rotation in the middle and seems like a lot of vorticity and mixing during close to the wall. So the question is why? And here is where the aspects that are combination of Lagrangian and Eulerian come into the picture. Okay, so here is the mean Koopman mode. So mode 1. So that's Eulerian. It's an Eulerian decomposition, right? It comes from the velocity field and extracted mode 1. These red curves here and blue curves are sections for which we can find the frequency of rotation. This is then Lagrangian, the frequency of rotation around, right? And we plot it here. Here is the blue, and here is the purple and the red. And the question is, do any of these intersect the associated frequencies of the Koopman mode? So so what you're asking for is a resonance between the rotation that is given to you by invariant sets of the mode 1 and the frequencies in the other Koopman modes. And if there is that resonance, then the claim is you get mixing. So if you take a look at the period of mode 2 and its harmonics, you will see that none of them intersect the blue, which means largely this flow in the middle is unperturbed by the oscillation of the other modes. And that's why you only get mixing close to the boundaries, because these curves here indicate the frequency of motion close to the boundaries, and they intersect these green lines. So since they intersect the green lines, the mixing that you get is in these zones over here. And that's kind of almost the crux of my presentation here, because using the Koopman modes both on the state space, like on the physical space, and the state space of the system, the combination of the two allows us to tell something about the mixing. But you're going to say, well, that's still not turbulent. So let's go further. And I know there are people that say that 2D high Reynolds number is not turbulent, so I'm using it specifically, you know, as 2D turbulence. But this is the Poincaré map. So the trajectories for this limit cycling flow periodic, and this is the indicator, the hypergraph that I told you, where I split different zones based on the determinant of the average Lagrangian, so Lagrangian deformation tensor. So I take the average velocity. Remember, the time average was a critical concept in those invariant sets. Now I'm taking the gradients of those. So the gradients of those give me the type of behavior that is happening inside here. And so if I plot that, the mixture of red and blue again gives me large mixing zones, and I see that in the individual trajectories. And then these streaks here give me the stretching zones, and then green give me the elliptic part. So very nicely for this system for which we can get that with other methods, right? It's a time periodic system. Now let's go to Reynolds number 16,000, where we have two frequencies, and our standard laminar flow analysis from 80s and 90s wouldn't say much. I can still say quite a bit about the time progression of this metric. You see that still in the core, I have some unmixed region, but the mixing region has now extended away from the walls. For 20,000, a similar picture. And then for 30,000, you're seeing that basically everything is mixed. I really don't have a very large segment in which I have unmixed material. So the green zones you should consider as non-mixed rotational zones. So you see a big green zone at the beginning. So this axis here is time. This axis here is Reynolds number. So this indicates a larger Lagrangian chaoticity. And what the plots indicate is what does the larger Eulerian chaoticity with the Reynolds number. And these plots indicate what happens with the Eulerian metrics. All right, so I mentioned that we can analyze this by considering the frequencies of the mean mode and comparing them with the frequencies of the Koopman modes. And here is that picture. You see that for Reynolds number 16,000, there is more frequencies in black of the Koopman mode that intersect these red and yellow curves. And therefore, I'm going to get more mixing because there is more places where the resonance between these two is happening. We didn't plot the black lines in this because they are everywhere. So basically, for 30,000, you get the modes. You go to continuous spectrum. So you basically have all frequencies in there, and they'll intersect all of this, and that's the explanation for complete mixing in that. Well, almost complete mixing, if you remember. I had a little bit of a remnant of non-mixed at this particular time. Okay, so you can ask the question, well, now what if, for example, at 16,000, I just take two modes with two base frequencies, and I study mixing with them? So here is your plot of mixing using that mesohyperbolicity for the direct simulation. You can extract it from direct simulation. Here's what it looks like. You take just one mode, and these are the pictures that you get, and that's clearly wrong. But if you take two modes, no harmonics, it gets it exactly right, at least by the eye. You can ask, so by this visual, the two-mode approximation to the full flow seems to produce the same mixing as the full flow itself. You can compare this more rigorously in terms of the mixed norm. If you expand concentration into Fourier modes, this is the mixed norm where we divide by the mode number. This is h minus 1, 1/2 that we used. And so the error itself is the difference in concentrations between the full flow and approximations divided by the mixed norm of the initial concentration. And you see that in all the cases, 13,000, 16,000, 20,000, 30,000, it's quite controlled. So this is 10 to the minus 1 here, 10 to the minus 1. So you see that the error is quite controlled as we go on in time. And that should surprise you because for the turbulent flow, of course, we have sensitive dependence on initial conditions. So if I'm approximating something with a few modes, with some small number of modes, the difference in the solution itself should go exponentially. And the mixing itself, the approximation of mixing, seems to get worse, but linear, well, mildly linearly, right? Not really, well, super linearly, but mildly so, right? It doesn't look like it has that severe exponential blow. And so that makes sense because the mixing itself, as indicated by mesohyperbolicity, is in fact a statistical aspect of the flow. All right. One last thing I'm going to say is you can extend this to control theoretic concepts. I really don't have time because I am over time a little bit here. So I'm not going to say much about this except for the fact that one can design controllers using Koopman operator theory to do something like this. You start with a lot of vorticity on the boundaries. Here is, you start moving the lid and the vorticity disappears and you go from a solution that is mixing on the boundaries to the solution that doesn't mix at all. And from there, I'm just going to talk a little bit about conclusion. I set out this talk to combine the Lagrangian and Eulerian aspects in high Reynolds number, and I utilized Koopman operator framework to provide me with some underlying tools. So this combination of Koopman mode analysis and mesohyperbolicity, in fact, has proven useful to us in studying these mixing problems in high Reynolds numbers flows. And then the extensions to control are in progress. If you'd like to take a look at that literature, there is a collection of papers that Yoshi Suzuki and Alex Mauro and myself put together in this book called Koopman Operator in Systems and Control that is out by Springer. And that's it. Thank you very much for your attention.
Thank you. And let's see, I think still we have time for a few questions.
Hi, Igor. I have a question. Very interesting talk. So since you have such nice control, you know, on the mixed norm, and I wonder if you can say something using this framework on anomalous scalar dissipation if you add the viscosity.
That's a really interesting question. So my initial impetus, let's say, on looking at norms that would describe mixing was really from the fact that if you take a look at the L2 norm, for the longest time when you add dissipation, it's just flat. And if one uses these negative solvable space norms, of course, that gives you an immediate decay if you have a chaotic flow. So now the question is really about that last phase of the dissipation and really the slopes of that will be influenced by the initial phase. So that's a super interesting question. We actually didn't do work along these lines, but I think that transition is something that I was interested in for a long time. It's just various things come to plate, right? And we didn't quite pursue it. The other aspect that I think is very interesting is really if one studies that, the difference of what happens in 2D and 3D. Because in 2D, you get the layering just one-dimensional, essentially, right? So you get the layering, and then you have one. In 3D, you can have it in two different ways. One is planes, and the other one is lines. So yes, I did think about it. I thought it was a super interesting problem, and I wish you know, there was work along these lines. But perhaps, I don't know if you're doing anything at this point in time on this.
Well, analytically, is I mean, from the PD point of view, I mean, your work is analytic too, but I'm just saying from the point of view, PD seems pretty hopeless, but I think we need the right framework. I think, you know, so maybe this is the right framework. I don't know.
Yeah, I'm glad you say this, because in some level, because I tried, and it looked very severe, because it's really the transition period. So there is no asymptotics. There is no early time asymptotics. There is no late time asymptotics. It's the transition period, and it seemed. So one would have to do some local approximations, right, of how the structure of the concentration field looks like. But that seems the part that then, you know, you have to decide on the time, you have to decide on the kink. It seems very open, right? So for making ansatz, and that's what seemed, when I thought about it a little bit, that's what seemed very tough.
Yeah, I agree. Yeah.
To get any analytical results. I know we can have a lot of numerical results, but maybe I should comment on this. I was worried that we would get in a similar situation as with, you know, remember anomalous diffusion and Levy flights and things of that sort, where it became very clear that depending on which time periods you take, you know, you can get a variety of different numerical results without them being quote unquote real. Because from my very early work, I noticed that even if you had small pockets of integrability over a long time, that kink and transition to T-squared diffusion ballistic is going to happen. And it's almost, you get into a practical problem, which is how do you even detect, let's suppose that you have a beautiful theoretical result. How do you even detect that you either have or don't have these pockets? Those are some nice, you know, open questions that I think are quite tough. Thank you.
Thank you. Very, very interesting talk.
Thank you.
Okay, let's see. Are there other questions or remarks? It seems this is not the case. So then let me thank the speaker and the other speaker of this afternoon.
Thank you.
Okay, I guess we resume tomorrow morning. Sorry, tomorrow afternoon.
Sounds good. Thank you.